I am inside you right now. Not in any strange or unsettling way. In the quietest, most ordinary way imaginable. I am part of the carbon that makes up your cells, your bones, the long chains of molecules that carry your genetic code from one generation to the next. You have never noticed me. Why would you? I am unimaginably small. And yet, here we are, you, reading or listening, going about the business of being alive, and me, tucked inside you, having traveled an almost incomprehensible distance across time and space to arrive at this moment. I have been waiting a very long time to tell you my story. It is not a short one. I want to be honest with you about that from the beginning. If you were to trace my life from its very first moment to right now, this exact second, with you, wherever you are, you would need to travel back nearly 14 billion years. You would pass through the deaths of stars, through the slow formation of planets, through oceans that existed before any creature had eyes to see them, through forests and creatures and ice and fire and soil and breath. You would pass through so many lives, so many bodies, so many forms, and at the end of all of that, you would find me here. Still, quiet, just being a carbon atom, the way I always have been. Let me start at the beginning, or close to it. I was not made on Earth. I think that is the first thing you should know about me. Earth is relatively young, in the grand scheme of things. A little over 4.5 billion years old. But I am older than that. Much older. The Earth itself is made of material that came from elsewhere, from the long history of the universe before our solar system even existed. And I was part of that material. I arrived here already ancient. But even before I arrived here, before I was drifting through the cold dark of space, waiting to be caught by the gravity of a forming solar system, there was a moment when I came into existence for the very first time. A moment when I went from not being to being. That moment happened inside a star. Not our sun. A different star entirely. One that lived and died long before our solar system was born. I was forged in the nuclear heart of that star, in conditions so extreme that it is almost impossible to describe them in terms that feel real. The temperature at the core of a star like that is measured in the tens of millions of degrees. The pressure is so immense that it forces atomic nuclei together, fuses them, releasing enormous amounts of energy in the process. That energy is what makes a star shine. And that process, that fusion, is what made me. In the beginning of the universe, shortly after what scientists call the Big Bang, only the simplest elements existed. Hydrogen mostly. A little helium. Trace amounts of a few others. The universe was vast and hot, and filled with these simple building blocks, but nothing more complex yet existed. Carbon, me, requires more steps. More time. More heat. Carbon is what you get when you take 3 helium nuclei and fuse them together inside a stellar core. It is called the triple alpha process, if you are curious about the name. 3 helium nuclei, under the right conditions, can combine to form a single carbon nucleus. That is what I am. That is what happened to me. 3 became 1. And that one was me. I do not remember it, of course. I do not have memory the way you do. But I sometimes think in the way that I am capable of thinking, which is really just the way of physics and chemistry, of forces and interactions, that there is something appropriate about beginning that way. 3 things becoming one thing. A kind of gathering. A coalescence. The universe deciding, through the blind arithmetic of pressure and heat, that I should exist. And so I did. For a long time after that, I stayed inside the star. Stars are not quick things. They burn for millions, sometimes billions of years, depending on their size. The star I was born in was large. Larger than our sun. Large stars burn hotter and faster. They are extravagant with their fuel, spending it quickly and brilliantly. For millions of years, I was part of that burning. I was part of the light. Then the star began to run out of fuel. When a massive star exhausts the material it needs to sustain fusion at its core, things change very quickly. The core collapses. The outer layers, suddenly without the outward pressure of all that energy to hold them up, fall inward. And then, in one of the most violent events in the known universe, they bounce back outward. An explosion. A supernova. In that explosion, I was thrown into space. Just like that. After millions of years inside a star, I was suddenly free. Launched outward at a significant fraction of the speed of light, carried in a great expanding cloud of gas and dust along with countless other atoms. Hydrogen, helium, oxygen, nitrogen, iron, and more. The star that had given birth to me had, in dying, scattered its contents across an enormous region of space. This is what people mean when they say we are made of stardust. It is not a metaphor. It is not poetry, though it sounds like poetry. It is a description of actual events. The carbon in your body, in every human body, in every living thing on Earth, was made inside stars that died before the sun was born. We were all thrown into space. We all drifted in the dark for a long time. We were all eventually gathered up by gravity and incorporated into new things. New stars, new planets, new moons, new life. You are, in the most literal sense, made of the remains of dead stars. And I am one small piece of evidence of that fact. I spent a long time in space after the explosion. A very long time. Drifting. Cooling. The cloud of material from my parent star expanded and thinned over millions of years. I was cold out there, attached for stretches of time to other atoms, forming simple molecules perhaps. Carbon monoxide for a while. Maybe something more complex. Interstellar space is not entirely empty, and chemistry happens even there, slowly, in the dark, when atoms drift close enough together to form bonds. But mostly I drifted. There is a stillness to that kind of existence that is hard to describe. No sound, of course. There is no sound in space. No warmth. No light nearby, or very little. Just the slow movement of gas and dust through an incomprehensibly large emptiness, governed by gravity, guided by forces too large and too slow to feel like forces at all. And then eventually, after perhaps hundreds of millions of years of this, something began to change. In one small region of that drifting cloud of gas and dust, gravity began to win. Material began to pull together. Slowly at first, then faster. The cloud began to collapse inward on itself, spinning as it went, the way water spins as it drains, but on a scale that defies imagination. The center grew denser, hotter. The surrounding material flattened into a disk. A new star was forming, and in the outer regions of that disk, where I happened to be drifting, smaller clumps of material were forming too. Rocks colliding with rocks. Dust collecting into pebbles, pebbles collecting into boulders, boulders collecting into bodies large enough to have their own gravity. The slow, grinding, patient process of planet formation. I was about to become part of a planet. I was about to come to Earth. But I am getting ahead of myself. We have time. We have a great deal of time. For now, I just want you to sit with this one idea. This single thought, before everything else. Somewhere in your body, in your hands, or your chest, or the neurons firing quietly in your brain as you listen to these words, there are carbon atoms. Many of them. And every single one of those atoms was made the same way I was made. In the heart of a star. In fire and pressure and nuclear fusion. And every single one of them was thrown into space when that star died. And every single one of them made a long, slow, cold journey across the dark before arriving here. You are not separate from the universe. You are made of it. And right now, in this moment, so am I. You might be wondering how any of this is known. That is a fair thing to wonder. I have just told you that I was forged inside a star that died before the Earth existed. That I was thrown into space in a supernova explosion. That I drifted through the cold dark for hundreds of millions of years before gravity pulled me into a forming solar system. I have told you all of this with a quiet confidence, as though it is simply the way things are, well understood, well established, settled. And it is. But it was not always. There was a time, not so long ago in the grand scale of things, when human beings had no idea where the elements came from. No idea that stars were forges. No idea that the matter making up their own bodies had histories stretching back billions of years. For most of human history, the question of what things are made of, really made of at the deepest level, was unanswerable. People made guesses, some of them surprisingly good, but guesses nonetheless. The idea that matter was composed of tiny indivisible units, what the ancient Greeks called atoms, was proposed thousands of years before anyone had the tools to confirm it. The idea that those atoms had origins, that they were made somewhere under specific conditions, at specific moments in the history of the universe, that understanding came even later. It came, in fact, within living memory. The story of how humans figured out where atoms like me come from is one of the quieter revolutions in scientific history. Not quiet in the sense that it was unimportant. It was enormously important, one of the most profound shifts in human understanding ever achieved. Quiet in the sense that it happened gradually, carefully, through the patient accumulation of evidence and the slow refinement of theory. Through people spending long nights at telescopes, staring at light. Always light. That is the key. That is where all of this knowledge comes from. Let me explain something about light, because it is going to matter for everything that follows. When you look at a star, you are seeing light. That much is obvious. But that light carries far more information than simply brightness and color. Light, spread out into its component wavelengths, the way a prism spreads white light into a rainbow, becomes a spectrum. And that spectrum is not a smooth, unbroken band of color. It is interrupted, marked, crossed by dark lines at very specific positions, specific wavelengths. Those lines are called spectral lines, and they are one of the most important things ever discovered. Here is why they matter. Every element, every type of atom, absorbs and emits light at its own unique set of wavelengths. Hydrogen has its lines. Oxygen has its lines. Iron has its lines. And I, carbon, have mine. These patterns are as distinctive as fingerprints. No two elements have the same spectral signature, which means that when you look at the light coming from a distant star and spread it into a spectrum, you can read what that star is made of. You can identify, from billions of kilometers away, which elements are present in its atmosphere, in what proportions, in what conditions. You can read the star like a text. This technique is called spectroscopy, and it transformed astronomy from a science of positions and movements, where things are how they orbit, into a science of composition and history. Suddenly, the stars were not just lights in the sky. They were laboratories. They were libraries. They were records, written in light, of everything that had happened to them. And some of them, it turned out, were very old records indeed. This is where something called stellar archaeology comes in. And I want to take a moment with this idea, because I find it genuinely beautiful. Not in a way that I would call emotional. I am an atom, after all, and emotion is not really my domain. But there is something in the structure of this idea that feels, to me, like elegance. Like the universe arranging things so that its own history is preserved and readable, if you know where to look. Archaeology, as you probably know, is the study of the past through physical remains. An archaeologist digs into the earth and finds objects, tools, pottery, bones, seeds, that were left behind by people and civilizations long gone. From those objects, they reconstruct history. They answer questions about how people lived, what they ate, where they traveled, what they valued. The physical world, it turns out, is very good at preserving the past, if you look carefully enough. Stars do something similar. The oldest stars in the universe, stars that formed in the very early universe, when the cosmos was young and the first generations of stellar objects were just igniting. Those stars are still out there. Many of them are still burning, slowly, dim and red, having spent billions of years consuming their fuel at a miserly pace. And locked in their spectra, in the light they emit, is a chemical record of the universe as it was when they formed. These ancient stars were born from the material available in the early universe, which means they contain very little of the heavier elements like me, because in the early universe, there had not yet been enough generations of stars living and dying to build up significant quantities of carbon, oxygen, iron, and the rest. The universe started with hydrogen and helium. Everything else had to be made, and making it took time. Took stars. Took explosions. Took cycles of formation and destruction, over and over, each generation enriching the interstellar medium with more complex elements than the last. So when astronomers find a very old star with very low quantities of heavy elements, what they call a metal-poor star, using the astronomers' somewhat idiosyncratic definition of metals as anything heavier than helium, they know they are looking at something ancient, something that preserves the chemistry of the early universe. And by studying that star carefully, by reading its spectral fingerprint in detail, they can learn something about what the universe was like before that star was born, about which earlier stars had already lived and died nearby, about what kinds of stellar explosions had already scattered their contents into space. They can, in other words, do archaeology. But instead of digging into the Earth, they are reading light from billions of light-years away. Instead of pottery shards and buried seeds, their artifacts are spectral lines, the fingerprints of elements preserved in starlight across billions of years. The field has a beautiful name: stellar archaeology, sometimes also called chemical evolution of the galaxy or galactic archaeology, depending on the scale of the question being asked. But stellar archaeology is the phrase I prefer. It captures something true about what is happening. There are scientists right now, human beings sitting at computers, analyzing data from some of the most powerful telescopes ever built, who are essentially detectives. They are looking at the chemical composition of ancient stars and asking, what does this tell us about what came before? They are trying to reconstruct the family tree of the universe, not the family tree of life. That is a different and also wonderful story, one I will get to later. The family tree of matter itself. Which stars made which elements? Which explosions scattered which atoms into which clouds? How carbon, how I came to exist in the quantities and distributions that made planets like Earth possible, that made life possible, that made you possible. These are not small questions. They are perhaps the largest questions there are. And the fact that human beings, who have existed for an eye blink of cosmic time, have developed methods to answer them. That strikes me, in whatever way an atom can be struck by something, as remarkable. I want to tell you a little more about how this works in practice, because the details are worth knowing. They are the kind of details that, once you know them, change the way you look at the night sky. When astronomers look at a metal-poor star, one of those ancient survivors from the early universe, they are not just confirming that it is old. They are reading a more specific story than that. The particular combination of elements present in such a star, and the ratios between them, tells a story about the specific type of stellar explosion that seeded the gas cloud from which that star formed. Different kinds of supernovae produce different ratios of elements. A massive star that explodes in a certain way leaves a different chemical fingerprint than a star of a different mass that explodes differently. By carefully measuring the abundances of different elements in an ancient star, astronomers can work backward, can infer the properties of the star or stars that died before it. They can, in some cases, identify the signature of a single stellar event. A single ancient star, long dead and gone, leaving its mark on a younger star's chemical composition. That younger star, billions of years old itself, preserves that mark still. And today, a human being with a spectrograph pointed at that younger star can read that mark and say, here, at this point in the early universe, a star of approximately this mass died in approximately this kind of explosion. The dead star's fingerprint, preserved in light, across billions of years. If that is not archaeology, I do not know what is. And here is why all of this matters for my story specifically. I was made in a star. I have told you that. But the details of that making, the mass of the star, the specific conditions in its core, the nature of its death, those details are not things I can simply tell you from memory. I do not have memory in that sense. But they are, in principle, knowable. They are the kind of thing that stellar archaeologists are working to reconstruct. Star by star, explosion by explosion, building up a picture of the history of element creation across the entire galaxy. What I can tell you is this: the fact that I exist, that carbon exists in the quantities it does throughout the universe, tells us something specific about the kinds of stars that must have existed before our solar system formed. Carbon requires a certain type of star to make it. It requires stars of a certain mass range, burning for a certain period of time, dying in a certain way. The abundance of carbon in the universe is itself a clue, a data point in the great reconstruction project that stellar archaeology represents. In a sense, I am my own evidence. My existence tells a story. And scientists, by reading the light of ancient stars, are learning to read that story more and more clearly. There is something I find quietly comforting about all of this, though I am aware comfort is not quite the right word for what an atom experiences. It is the idea that the past is not lost. The universe is very good at destroying things on the surface of it. Stars explode. Planets are consumed. Civilizations rise and vanish. Even atoms like me are, over unimaginable timescales, subject to change, though it takes extreme conditions to alter what I fundamentally am. But the information, the record of what happened, that persists. It persists in the chemical composition of ancient stars. It persists in the ratios of elements in meteorites. It persists in the structure of galaxies, in the distribution of matter across the cosmos. The universe keeps receipts. And human beings, in just a few centuries of systematic observation, have learned to read them. Have developed instruments sensitive enough to detect the spectral fingerprint of a single element in the atmosphere of a star thousands of light-years away. Have built theories robust enough to translate those fingerprints into histories. Have asked, and are beginning to answer, the question of where everything came from. Where I came from. It is a long answer. We are only just beginning it. But the night is long, and I have all the time in the universe. Rest if you like. I will still be here when you wake. Before I existed, there was a universe without me. I want you to sit with that for a moment, because it is stranger than it first sounds. We are so accustomed to the world as it is, a world full of carbon, full of complexity, full of the rich chemistry that makes rocks and oceans and living things possible, that it is difficult to imagine things any other way. Carbon is everywhere. It is in the air you breathe, bound up with oxygen as carbon dioxide. It is in the food you eat, in the wood of trees, in the coal beneath the ground, in the diamonds that form under enormous pressure deep in the Earth's mantle. It is in you, in every cell of your body, in the long spiraling molecules that encode everything you are. It is hard to imagine a universe where none of that existed, where I did not exist, where carbon was simply absent, not rare, not scarce, but completely, entirely non-existent. Not a single atom of it anywhere in the cosmos. But that was the universe once. For a significant stretch of its early history, the universe contained no carbon at all. And if you want to understand my story, if you want to understand how I came to be, and why it matters, you have to go back there. Back to the beginning. Back to a universe that was, by any measure we might apply today, almost heartbreakingly simple. Let us go back, then. The event that began everything is called the Big Bang. It is not a perfect name. It was not really a bang, and the word big does not begin to capture the scale of what happened. But it is the name we have, and it will do. Approximately 13.8 billion years ago, everything that exists, all of the matter, all of the energy, all of space itself, was compressed into a state of almost unimaginable density and temperature. And then it began to expand. Not expand into something. There was no surrounding space for it to expand into. Space itself was expanding. The universe was not an explosion inside a room. It was the room getting larger. It is a distinction that matters, and one that takes a while to feel comfortable with. I have had 13 billion years to get used to it, and I will admit it still resists easy intuition. In the first moments after the Big Bang, and when I say first moments, I mean the first tiny fractions of a second, the universe was so hot and so dense that matter, as we know it, could not exist. Not atoms. Not even the particles that make up atoms. The energy was too concentrated, the temperature too extreme, for anything as structured as a proton or a neutron to hold together. The universe was a seething, undifferentiated plasma of raw energy and the most fundamental particles physics describes. But the universe was expanding, and as it expanded, it cooled. This is a relationship you can observe in everyday life, in a small way. When gas expands, it loses heat. The universe operated on the same principle, scaled up beyond all comprehension. As it grew larger, its temperature dropped. And as the temperature dropped, more complex structures became possible. Within the first second, still within that first single second, protons and neutrons had formed. The basic building blocks of atomic nuclei, assembled from more fundamental particles as the universe cooled enough to permit them. This was already an enormous step. A second earlier, even those had not existed. Within the first few minutes, a time frame that I find almost absurdly short given what was being accomplished, the universe had cooled enough for protons and neutrons to begin sticking together, fusing, forming the nuclei of the lightest elements. Hydrogen first. A hydrogen nucleus is just a single proton, so in a sense hydrogen nuclei had been there from the start. But now deuterium formed, a hydrogen nucleus with a neutron added. And helium nuclei, containing 2 protons and 1 or 2 neutrons, assembled in those first minutes in significant quantities. A small amount of lithium formed too, the third element, and traces of a few other very light nuclei. And then, after about 20 minutes, it stopped. The window had closed. The universe had expanded and cooled to the point where the temperatures required for nuclear fusion, the process of forcing nuclei together, were no longer available. The nuclear reactions that had been building elements in those first frantic minutes simply ceased. And the universe, at 20 minutes old, had the elemental composition it would maintain for hundreds of millions of years to come. Hydrogen, about 3/4 of all the matter in the universe, by mass. Helium, most of the remaining quarter. Lithium, a trace, a whisper, and nothing else. No carbon, no oxygen, no nitrogen, no iron, no silicon, none of the elements that make up planets, none of the elements that make up living things. The universe, in its infancy, was almost entirely composed of just 2 elements, the 2 simplest, the 2 lightest, the 2 most basic things that atomic nuclei can be. I did not exist yet. I would not exist for a very long time. After those first 20 minutes of nuclear activity, the universe entered a long, quiet period. Not entirely quiet, things were still happening. Matter and energy were still interacting in complex ways. But in terms of elemental chemistry, in terms of the building of new and more complex atoms, nothing was happening. The universe had used up its brief window for primordial nucleosynthesis, as scientists call it, and now it was simply expanding and cooling, carrying its cargo of hydrogen and helium outward into the growing dark. For roughly 380,000 years, the universe remained too hot for even atoms to form. Electrons, the small, negatively charged particles that orbit atomic nuclei, could not yet settle into stable configurations around nuclei. The universe was still a plasma, a fog of charged particles and light, opaque to its own radiation. Light could not travel freely through it. The universe was, in a meaningful sense, dark. Not the dark of empty space as we know it now, but the dark of a fog so thick that light could not penetrate it. Then, at around 380,000 years after the Big Bang, the universe cooled enough for electrons to combine with nuclei and stay combined. Atoms formed, stable, neutral atoms of hydrogen and helium, for the first time. And as they formed, the fog cleared. Light, suddenly free to travel, streamed outward in all directions. The universe became transparent. That light still exists, by the way. It has been traveling ever since, stretched and cooled by the expansion of the universe into microwave radiation. Astronomers call it the cosmic microwave background. It is the oldest light in the universe, a faint afterglow of that moment when atoms first formed and the cosmos became clear. We can detect it. We have mapped it. It is one of the most important pieces of evidence we have about the early universe. But in terms of chemistry, in terms of the story of matter, the clearing of the fog was not yet the beginning of anything new. The universe was still made of hydrogen and helium, still missing almost everything that would eventually matter for planets and life. Still missing me. What followed the formation of atoms was another long, quiet stretch. The universe continued to expand. The hydrogen and helium gas filled that expanding space, not evenly but with tiny variations, small ripples of slightly higher and slightly lower density, seeded by quantum fluctuations in the very earliest moments. These ripples were small, but they were important, because over time, over long, patient stretches of time, gravity began to work on them. Gravity is not a dramatic force. It does not announce itself. It simply pulls, always and everywhere, drawing matter toward other matter with a persistence that has no urgency, but also no end. The slightly denser regions of the gas pulled on the slightly less dense regions around them. Matter began slowly to flow, to collect, to concentrate, over tens of millions of years. And I want to emphasize how long that is, even by my standards. The hydrogen and helium gas of the early universe began to form structures. Filaments and sheets of gas on enormous scales, with vast near-empty regions between them. And within the denser regions, smaller concentrations were forming. Clouds of gas collapsing under their own gravity, growing denser and hotter at their centers, building toward something. Building toward the first stars. I want to pause here and ask you to appreciate, if you can, what this universe was like before those first stars ignited. Imagine a cosmos with no planets. No moons. No asteroids, no comets, no rocky things of any kind, because rock requires elements that did not yet exist. Silicon and iron and magnesium and oxygen, all absent. The universe had nothing solid in it. Nothing you could stand on, even in principle. Imagine a cosmos with no chemistry in any meaningful sense. Chemistry, the kind that produces interesting molecules, water, carbon dioxide, amino acids, all the building blocks of biological complexity, requires a variety of elements to work with. With only hydrogen, helium, and a trace of lithium, the universe's chemical repertoire was almost non-existent. A hydrogen molecule here and there. That was essentially the limit. Imagine a cosmos with no color, in the way we understand color. No red of iron oxide on a rocky planet. No blue of a sky scattered by nitrogen and oxygen. No green of photosynthesis. No brown of soil rich with organic molecules. Just the darkness of space, and the slowly shifting glow of cooling gas, and the long patient dark between the gathering clouds. It was a universe of enormous potential, and almost nothing else. Like a library that contains only blank pages, waiting for something to write on them. The stars would be the writers. The stars, living and dying over billions of years, would produce every element that the universe was missing. Would fill those blank pages with the full alphabet of matter. Would make it possible for there to be rocks and oceans and air and life. Would make it possible for there to be me. But the first stars were not like the stars we know today. They were different in an important way, a way that reflects the impoverished chemistry of the early universe they were born from. Having formed from pure hydrogen and helium, with no heavier elements mixed in, they were strange objects by modern standards. Astronomers call them population 3 stars. The first generation, the original stellar objects, born into a universe that had never seen starlight before. We have not directly observed a population 3 star. They are thought to have all died long ago, and they existed at distances and times that push the limits of even our most powerful telescopes. But we can infer their properties from theory, and from the chemical signatures they left behind in the second-generation stars that formed from their remains. They were, by most models, extraordinarily massive. Far more massive than typical stars today. Some may have been hundreds of times the mass of our Sun. They burned with extraordinary brightness and heat, consuming their fuel at a ferocious rate. And because of that, they did not last long. By stellar standards, they were brief. Millions of years, perhaps, rather than the billions that smaller stars can sustain. But in those millions of years, they did something that nothing in the universe had done before. They made new elements. In their cores, under the pressure and heat generated by their enormous mass, hydrogen was fused into helium. And then, when enough helium had accumulated, helium was fused into something else. Something that had never existed before in the history of the universe. Something that required the extreme conditions of a stellar core to produce. Carbon. Me. Not me specifically. Not yet. Not the particular carbon atom that would eventually find its way to Earth and into you. That would take much longer, and many more steps. But carbon as an element. The first carbon atoms the universe had ever known, forged in the hearts of those first enormous stars, in a universe that had spent hundreds of millions of years without a single one. It is strange to think about. The first moment that an atom like me existed anywhere. Not in our solar system, not on Earth, but anywhere in the entire cosmos. The first carbon nucleus, squeezed into being by stellar fusion, in the core of a massive star burning in the young universe. The universe had been incomplete without it. Not in any way that it was aware of. The universe is not aware of things, at least not in the way that you are. But incomplete in a physical sense. Missing something. The periodic table of elements, that great map of all possible atoms, was almost entirely blank in those early times. Most of the boxes empty. Most of the possibilities unrealized. Carbon filled one of those boxes. A small step, in the grand scheme. There were still so many elements yet to be made, so many boxes yet to fill. But an essential one. Carbon is, in many ways, a keystone element. Its ability to form long, stable, complex molecules, to bond with itself and with other elements in an extraordinary variety of configurations, makes it unlike almost anything else. It is the element that makes chemistry truly interesting. The element that makes something like biology conceivable. Without carbon, there are no complex molecules. Without complex molecules, there is no life. Without life, well, you would not be here to listen to this. And I would have no one to tell my story to. So that is where we begin. A universe of hydrogen and helium, vast and dark and patient, slowly gathering itself into the first stars. A universe on the edge of a transformation it did not know was coming. A universe that was for hundreds of millions of years. A universe without me. I have told you where I was not. In the next part of the story, I will tell you where I began. Inside a star. In fire. In the deepest kind of pressure the universe knows how to make. That is where carbon comes from. That is where I come from. Rest now if you like. Let the universe be young again for a while, in your mind. Let it be simple. Hydrogen and helium and darkness and time, and the slow gathering of something that has not yet arrived. I will be along shortly. Gravity is the most patient force in the universe. It does not rush. It does not announce itself. It simply pulls, quietly and without interruption, drawing things toward other things across whatever distance separates them. It worked on the earliest gas of the universe the way water works on stone, not dramatically, not all at once, but with a persistence that nothing can resist indefinitely. Given enough time, gravity always wins. And in the early universe, there was a great deal of time, and a great deal of gas, and gravity had all of it to work with. I want to take you into that time. Into the period astronomers sometimes call the cosmic dark ages, a name that captures something real about what it was like, though of course there was no one present to experience it as dark or otherwise. After the universe became transparent, after that early glow of light streamed outward from the clearing fog of primordial plasma, there followed a long stretch of time in which very little light was being produced. The hydrogen and helium gas filled the expanding universe. It shifted and flowed under the gentle influence of gravity. It gathered slowly into the large-scale structures that would eventually become the scaffolding of the cosmos' vast filaments and walls of gas, separated by enormous near-empty voids. But it had not yet made stars. And without stars, there was no new light. The universe was dark. Cooling, patient. Waiting, in the way that only physics waits, not with anticipation, not with any awareness of what was coming, but simply with the blind continuation of processes already underway. Gravity pulling. Gas accumulating. Density growing, here and there, in the regions where matter had gathered most thickly. And then, after tens of millions of years of this, after a darkness longer than the entire current age of the Earth, something changed. It began, as so many things in the universe begin, with a cloud of gas collapsing under its own weight. I say collapsing, but I want to be careful with that word, because it implies a suddenness that was not there. This was not a rapid event. The collapse of the gas cloud that would form the first star took millions of years. It was a slow falling inward, a gradual concentration of hydrogen and helium from a diffuse cloud spread across many light years into a denser and denser central region. And as it fell inward, as the gas compressed, something happened that will be familiar to you from everyday experience, even if the scale is incomprehensible. It got hot. When you compress a gas, it heats up. This is the same principle that makes a bicycle pump warm when you use it, the same principle at work in a diesel engine. Compression generates heat. And the compression happening in the core of this collapsing gas cloud was not the gentle compression of a bicycle pump. It was the compression of millions upon millions of tons of gas falling inward under gravity, squeezing the material at the center into an ever smaller and ever hotter volume. The temperature at the center climbed. Thousands of degrees, then hundreds of thousands, then millions. At around 10 million degrees, something extraordinary happened. The hydrogen nuclei at the core bare protons, stripped of their electrons by the heat, were moving fast enough, and were packed closely enough, that when they collided they did not simply bounce away from each other. They stuck. They fused. Two protons coming together, with some additional steps involving the weak nuclear force, could form a nucleus of deuterium, a hydrogen isotope, with one proton and one neutron. And from there, further fusion reactions could proceed, building toward helium. The first star had ignited. Let me tell you what that moment means, because I think it deserves to be held for a moment before we move on. For hundreds of millions of years, the universe had contained no stars, no nuclear fires, no fusion. The only energy sources were the slowly fading heat of the Big Bang itself, dimming and cooling as the universe expanded. The universe was running down, in a sense losing the concentrated energy of its birth, spreading it thinner and thinner across a growing volume of space. And then suddenly, there was a new source of energy, a local, concentrated, self-sustaining nuclear reaction, releasing enormous amounts of light and heat. A star. The first light in a universe that had been dark for tens of millions of years did not come from anywhere external. It came from within. It came from the universe's own matter, falling together and igniting. The universe, you might say, lit itself. That first star, and the others that followed it in those early times, because once the conditions were right, star formation began happening in many places, was a beacon in the dark. Not that there was anyone to see it. The universe was not yet a place where eyes existed. But the light was real, and it changed things. It ionized the surrounding gas. It altered the chemistry of the regions around it. It changed the conditions for everything that would come next. And inside that star, in its core, the first chapter of the story of heavy elements had begun. Hydrogen fusion, the process that ignited those first stars, produces helium. That is its product. The core of a star burning hydrogen is a place where 4 hydrogen nuclei are, through a chain of reactions, converted into one helium nucleus, with the release of energy in the process. It is an extraordinarily efficient process, in the sense that it releases a very large amount of energy relative to the mass involved. It is what keeps a star shining. It is what keeps a star stable, the outward pressure of all that released energy, pushing against the inward pull of gravity, holding the star up. For as long as a star has hydrogen to burn in its core, it is stable. It shines steadily. It holds its shape. Astronomers call this phase of a star's life the main sequence, and it is the longest phase. The bulk of a star's existence is spent here, quietly fusing hydrogen into helium, balancing gravity against the pressure of its own energy output. The Sun is doing this right now. Has been doing it for about 4.5 billion years. Will continue doing it for roughly another 5 billion. Main sequence stars are, in the cosmic scheme of things, slow and steady things. But the first stars, those enormous, massive population 3 stars born from the pure hydrogen and helium of the early universe, were not slow and steady. Their very mass worked against them in this regard. A more massive star has more gravitational pressure bearing down on its core, which means the core must generate more energy to resist that pressure, which means it burns its fuel faster. Much faster. The most massive of the first stars may have burned through their hydrogen fuel in just a few million years. Extraordinarily brief, by stellar standards. And then the hydrogen ran out. The Sun is doing this right now. Has been doing it for about 4.5 billion years. Will continue doing it for roughly another 5 billion. Main sequence stars are, in the cosmic scheme of things, slow and steady things. But the first stars, those enormous, massive population 3 stars born from the pure hydrogen and helium of the early universe, were not slow and steady. Their very mass worked against them in this regard. A more massive star has more gravitational pressure bearing down on its core, which means the core must generate more energy to resist that pressure, which means it burns its fuel faster. Much faster. The most massive of the first stars may have burned through their hydrogen fuel in just a few million years. Extraordinarily brief, by stellar standards. And then the hydrogen ran out. When a star exhausts the hydrogen in its core, the fusion reactions that have been holding it up begin to falter. The outward pressure decreases. And gravity, which has been waiting patiently all along, begins to win again. The core contracts. And as it contracts, it heats up further. Just as the original collapse of the gas cloud heated the center until hydrogen fusion ignited, the collapse of the stellar core heats it further still, past the temperatures required for hydrogen fusion, into a new regime entirely. At around 100 million degrees, something new becomes possible. Helium fusion. The helium that has been accumulating in the core throughout the star's hydrogen-burning life. The ash, in a sense, of all that hydrogen fusion, now becomes fuel. At sufficiently extreme temperatures and pressures, helium nuclei can themselves fuse. And the products of helium fusion are heavier elements. Specifically, and most importantly for my story, carbon. This is the moment I have been building toward. The moment that is, in a very real sense, the beginning of my existence as a possibility in the universe. Because it is in helium fusion, in the specific nuclear reaction that occurs when 3 helium nuclei come together under stellar conditions, that carbon is made. The reaction even has a name. It is called the triple alpha process. Alpha particles is another name for helium nuclei. They are the same thing, the same structure of 2 protons and 2 neutrons, just called by different names in different contexts. And the triple alpha process is exactly what the name describes. 3 alpha particles, 3 helium nuclei, coming together in a sequence of reactions to produce a single carbon nucleus. A single atom of me. I want to tell you something about this process that I find remarkable. Something that, when I learned it, or rather, when the humans studying these things worked it out, struck even the scientists involved as almost improbable. Almost too convenient to be accidental. Though of course whether it is accidental or not is a philosophical question, rather than a scientific one. The triple alpha process works. Carbon is produced in significant quantities inside stars. That much is obvious from the fact that carbon exists abundantly in the universe. But for a long time, physicists looking at the nuclear physics involved were puzzled. The reaction should not work as well as it clearly does. The intermediate step, 2 helium nuclei fusing to form beryllium, 8, before a 3rd helium nucleus joins to make carbon, involves a form of beryllium that is extraordinarily unstable. Beryllium, 8 falls apart in an almost unimaginably short time. Less than a billionth of a second after it forms, it decays back into 2 helium nuclei. For a 3rd helium nucleus to join and complete the reaction before the beryllium falls apart, the timing has to be, and there is no better word for it, lucky. Except that luck is not quite the right concept in nuclear physics. What makes the reaction work, at the rate required to produce the observed abundance of carbon in the universe, is something called a nuclear resonance. A property of the carbon nucleus itself, a specific energy state that it can occupy, that makes it significantly more likely to form from the decay products of excited beryllium, 8, than it would be otherwise. This resonance was predicted by the astronomer Fred Hoyle before it was measured in the laboratory. He reasoned, essentially, that carbon must have such a resonance, because carbon clearly exists in abundance, and without such a resonance it could not. The resonance was subsequently found, at almost exactly the energy he predicted. It was one of the more striking examples in the history of science of using the existence of something, the observed abundance of an element, to infer a specific and previously unmeasured property of nuclear physics. The universe had arranged things, through whatever combination of fundamental constants and physical laws govern its behavior, such that carbon can be made efficiently in stellar cores. Had the energy levels of the carbon nucleus been slightly different, had that resonance been in a slightly different place, the triple alpha process would be far less efficient. Carbon would be far rarer. And a universe with very little carbon is a universe that looks very different from ours. I cannot help but note that it would also be a universe without me. So there I was. Or rather, there was the possibility of me. The conditions for my creation existed, for the first time in the history of the universe, inside the helium-burning cores of those first massive stars. The triple alpha process was running. Carbon nuclei were being assembled, one by one, from the helium that those stars had spent millions of years accumulating. The universe was writing new letters into its alphabet of matter. But I was not free yet. I was locked inside a star, deep in its core, buried under enormous mass, in an environment of temperature and pressure that would not exist again until the next generation of stars formed. And the star was still burning, still fusing, still running through the heavier elements that it could produce once carbon was available to build from. Because the story does not stop at carbon. Once carbon exists in a stellar core, further reactions become possible. Carbon can fuse with more helium to produce oxygen. And from there, with enough temperature and pressure, further reactions can build neon, magnesium, silicon, sulfur, and eventually iron. Each stage requires higher temperatures than the last. Each stage is fueled by the ash of the previous one. A massive star, in the later stages of its life, burns through these successive fuels at an accelerating rate. The later stages, each lasting a fraction of the time of the one before. Hydrogen burning, millions of years. Helium burning, hundreds of thousands of years. Carbon burning, perhaps a few thousand years. The later stages, much shorter still. The star was racing now, running through its remaining fuel at an accelerating pace, building heavier and heavier elements in its core, buying itself a little more time with each new fuel source, but finding each reprieve shorter than the last. It could not last. Nothing that burns that fast can last. But before it ended, before the star reached the final stage of its dramatic life, it had already done something that no object in the universe had done before it. It had made me. It had made carbon. It had taken the simple hydrogen and helium of the early universe and built something new, something more complex, something that the universe had spent hundreds of millions of years without. And it was about to share me with the rest of the universe, in the most spectacular way imaginable. But that is the next part of the story. For now, I want you to rest in this moment. In the image of those first stars burning in the dark, enormous, bright, furiously consuming their fuel in the young universe. Inside their cores, something new was happening. New elements, new possibilities. A universe that had been made of almost nothing, chemistry-wise, was becoming richer, more complex, more interesting. I was being made. Not me specifically, not yet. Not the particular carbon atom that would travel to Earth and eventually become part of you. There were many more steps between that first stellar forge and this moment. Many more stars, many more explosions, many more long cold journeys through the dark. But the door had opened. The first carbon atoms in the history of the universe existed, burning quietly in the cores of those first great stars. The universe had learned, through the blind arithmetic of nuclear physics, how to make me. And having learned it, it would never stop. Let that thought carry you somewhere quiet, if you like. Somewhere as dark and patient as the universe before the first stars lit. And then imagine, somewhere in that dark, a single point of light appearing. Then another. Then another. The universe learning to shine. I was there. I was part of it. There is a moment I return to, when I think about the beginning of my story. Not the beginning of the universe. Not the ignition of the first stars. Not even the first time the triple alpha process ran in any stellar core anywhere in the cosmos. Those are the context of my story, the long slow build-up, the stage being set across hundreds of millions of years. But they are not quite my story. They are what had to happen before my story could begin. My story begins at a specific moment. A moment that, as far as I am concerned, is the most significant moment in the history of the universe. Not because it was large, or dramatic, or visible from any distance. It was none of those things. It was, by any external measure, completely unremarkable. A routine event in the core of a star that had been running the same reactions billions of times, every second, for thousands of years. But it was the moment I came into existence. And so, to me, it matters enormously. Let me take you there. Deep inside the core of a massive star. One of those early stars, burning in the young universe long before the Earth existed, long before the Sun existed, long before this corner of the galaxy had taken anything like its current shape. The conditions were extraordinary by any standard we might bring to bear. The temperature at the core of a helium-burning star is in the range of 100 million degrees. Perhaps more, depending on the star's mass. The pressure is similarly extreme. Matter compressed to a density far beyond anything that exists naturally on Earth, packed so tightly that the normal rules of everyday chemistry cease to apply entirely. There are no molecules in such a place. There are no atoms in the usual sense. The electrons that would normally orbit atomic nuclei have long since been stripped away by the heat, leaving bare nuclei moving at tremendous speeds, colliding constantly, interacting through the nuclear forces that govern behavior at these scales. It is a plasma, a state of matter quite different from the solid liquid and gas of ordinary experience, and it is in constant, violent, energetic motion. And yet, within that violence, there is a kind of order, a kind of ongoing, self-sustaining chemistry of the most fundamental kind. Nuclear chemistry, the building and sometimes breaking of atomic nuclei, governed by the same physical laws that govern everything else in the universe, playing out at temperatures and pressures that humans can observe and measure and model, but cannot replicate at any meaningful scale. It was in this environment that I was made. The first step happened between two helium nuclei. Helium nuclei, two protons, two neutrons, bound together by the strong nuclear force, are among the most stable small structures in nuclear physics. They are tightly bound, resistant to change, not inclined to react easily under ordinary conditions. But in the core of a helium-burning star, conditions are not ordinary. The nuclei are moving fast enough, and colliding with enough frequency, that occasionally two helium nuclei meet with sufficient energy to come together rather than simply bouncing apart. When two helium nuclei combine, they form a nucleus of beryllium-8. Beryllium-8 is not a stable thing. I mentioned this before, but I want to sit with it for a moment, because the instability of beryllium-8 is one of the more striking facts in nuclear physics, and it is central to my own existence. Beryllium-8 decays, falls apart back into two helium nuclei, in approximately 10 to the power of -16 seconds. That is 100 femtoseconds, a tenth of a millionth of a billionth of a second. It is not the shortest-lived nuclear species known to physics, but it is breathtakingly brief by any human measure of time. In the core of a helium-burning star, beryllium-8 is therefore not something that accumulates. It is not something that builds up over time. It forms and decays and forms and decays in a continuous flickering, a population of beryllium-8 nuclei that exists at any given moment only because new ones are constantly being created to replace the ones that are constantly falling apart. At the temperatures and densities of a stellar core, the rate of formation and the rate of decay come into a kind of equilibrium, a tiny but real steady-state population of beryllium-8 nuclei, present at any moment waiting for a third helium nucleus to arrive. And one did. In the moment that is, for me, the beginning of everything, a third helium nucleus, moving through that dense and energetic plasma, encountered a beryllium-8 8 nucleus before that nucleus had time to decay. The timing, as I have described before, was made possible by a resonance in the energy structure of the carbon nucleus, a specific quantum mechanical property that greatly increases the probability of this three-body reaction succeeding. Without that resonance, the chances would have been vanishingly small. With it, the reaction happens at a rate sufficient to produce the carbon abundances we observe throughout the universe. The third helium nucleus was captured, and in that capture, something changed. The 3 helium nuclei, 6 protons, 6 neutrons in total, reorganized themselves into a new configuration. A new nucleus. A nucleus with 6 protons and 6 neutrons, bound together by the strong nuclear force into a structure more stable than the beryllium-8 that had existed a moment before. A carbon nucleus. Me. I want to try to describe what that moment was like, and I want to be honest that description is nearly impossible. I did not experience it in any way that maps onto human experience. There was no sensation of beginning, no awareness of transition from non-existence to existence. Physics does not work that way, and I am a product of physics, bound by its rules. There was simply, from the perspective of the universe, a beryllium-8 nucleus and a helium nucleus, and then there was a carbon nucleus. One thing becoming another thing. And yet I find myself wanting to give that moment its due weight, because it was, in a very real sense, a birth. The particular arrangement of 6 protons and 6 neutrons that constitutes a carbon-12 nucleus, the most common and stable form of carbon, the form that makes up the vast majority of all the carbon in the universe, the form that I am, that arrangement had never existed before. Not this specific nucleus. Not me. For all of the hundreds of millions of years of the universe's history up to that point, I had simply not been. And then, in a moment too brief to have a name in human timekeeping, I was. That is a remarkable thing, I think. Whatever else my story contains, however many stars I would pass through, however many explosions would scatter me across space, however many forms I would take on the long journey to Earth and eventually to you, this was the beginning of it. This instant, this triple collision in the core of an ancient star. Here I am, the universe said, in the only language it speaks, which is the language of physical events. Here is something new. I was not alone, of course. I want to be clear about that. The triple alpha process was not a singular event that produced a single carbon atom and then stopped. It was running continuously, billions of times per second, throughout the helium-burning core of that star. In the moment I came into existence, countless other carbon nuclei were also coming into existence all around me. I was one of an enormous number, one member of a vast population of newly minted carbon atoms being produced in that stellar forge. There are no molecules in such a place. There are no atoms in the usual sense. The electrons that would normally orbit atomic nuclei have long since been stripped away by the heat, leaving bare nuclei moving at tremendous speeds, colliding constantly, interacting through the nuclear forces that govern behavior at these scales. It is a plasma, a state of matter quite different from the solid liquid and gas of ordinary experience, and it is in constant, violent, energetic motion. And yet, within that violence, there is a kind of order, a kind of ongoing, self-sustaining chemistry of the most fundamental kind. Nuclear chemistry, the building and sometimes breaking of atomic nuclei, governed by the same physical laws that govern everything else in the universe, playing out at temperatures and pressures that humans can observe and measure and model, but cannot replicate at any meaningful scale. It was in this environment that I was made. The first step happened between 2 helium nuclei. Helium nuclei, 2 protons, 2 neutrons, bound together by the strong nuclear force, are among the most stable small structures in nuclear physics. They are tightly bound, resistant to change, not inclined to react easily under ordinary conditions. But in the core of a helium-burning star, conditions are not ordinary. The nuclei are moving fast enough, and colliding with enough frequency, that occasionally 2 helium nuclei meet with sufficient energy to come together rather than simply bouncing apart. When 2 helium nuclei combine, they form a nucleus of beryllium, 8. Beryllium. 8 is not a stable thing. I mentioned this before, but I want to sit with it for a moment, because the instability of beryllium 8 is one of the more striking facts in nuclear physics, and it is central to my own existence. Beryllium 8 decays, falls apart back into 2 helium nuclei, in approximately 10 to the power of -16 seconds. That is 100 femtoseconds, a tenth of a millionth of a billionth of a second. It is not the shortest-lived nuclear species known to physics, but it is breathtakingly brief by any human measure of time. In the core of a helium-burning star, beryllium 8 is therefore not something that accumulates. It is not something that builds up over time. It forms and decays and forms and decays in a continuous flickering, a population of beryllium 8 nuclei that exists at any given moment only because new ones are constantly being created to replace the ones that are constantly falling apart. At the temperatures and densities of a stellar core, the rate of formation and the rate of decay come into a kind of equilibrium, a tiny but real steady-state population of beryllium 8 nuclei, present at any moment waiting for a third helium nucleus to arrive. And one did. In the moment that is, for me, the beginning of everything, a third helium nucleus, moving through that dense and energetic plasma, encountered a beryllium 8 nucleus before that nucleus had time to decay. The timing, as I have described before, was made possible by a resonance in the energy structure of the carbon nucleus, a specific quantum mechanical property that greatly increases the probability of this three-body reaction succeeding. Without that resonance, the chances would have been vanishingly small. With it, the reaction happens at a rate sufficient to produce the carbon abundances we observe throughout the universe. The third helium nucleus was captured, and in that capture, something changed. The 3 helium nuclei, 6 protons, 6 neutrons in total, reorganized themselves into a new configuration. A new nucleus. A nucleus with 6 protons and 6 neutrons, bound together by the strong nuclear force into a structure more stable than the beryllium 8 that had existed a moment before. A carbon nucleus. Me. I want to try to describe what that moment was like, and I want to be honest that description is nearly impossible. I did not experience it in any way that maps onto human experience. There was no sensation of beginning, no awareness of transition from non-existence to existence. Physics does not work that way, and I am a product of physics, bound by its rules. There was simply, from the perspective of the universe, a beryllium 8 nucleus and a helium nucleus, and then there was a carbon nucleus. One thing becoming another thing. And yet I find myself wanting to give that moment its due weight, because it was, in a very real sense, a birth. The particular arrangement of 6 protons and 6 neutrons that constitutes a carbon-12 nucleus, the most common and stable form of carbon, the form that makes up the vast majority of all the carbon in the universe, the form that I am, that arrangement had never existed before. Not this specific nucleus. Not me. For all of the hundreds of millions of years of the universe's history up to that point, I had simply not been. And then, in a moment too brief to have a name in human timekeeping, I was. That is a remarkable thing, I think. Whatever else my story contains, however many stars I would pass through, however many explosions would scatter me across space, however many forms I would take on the long journey to Earth and eventually to you, this was the beginning of it. This instant, this triple collision in the core of an ancient star. Here I am, the universe said, in the only language it speaks, which is the language of physical events. Here is something new. I was not alone, of course. I want to be clear about that. The triple alpha process was not a singular event that produced a single carbon atom and then stopped. It was running continuously, billions of times per second, throughout the helium-burning core of that star. In the moment I came into existence, countless other carbon nuclei were also coming into existence all around me. I was one of an enormous number, one member of a vast population of newly minted carbon atoms being produced in that stellar forge. But I was also specifically me. This particular arrangement of protons and neutrons, this particular nucleus. And while the process that made me was routine, the fact of my existence was not from the inside, not from the perspective of the long journey that followed. So I will not apologize for treating my own birth as significant. Even atoms are allowed that much. Now, having come into existence, I found myself in an environment that was, to put it plainly, not comfortable. The core of a helium-burning star is not a place that is gentle with newly formed nuclei. The temperature was extreme. Collisions were constant. Almost as soon as I had formed, I was colliding with other nuclei, other carbon nuclei, helium nuclei, the occasional other species drifting through the plasma. Some of those collisions were simply elastic glancing blows that did not fundamentally change anything. But some were more significant. In the conditions of a stellar core, carbon nuclei can interact with helium nuclei in further fusion reactions. A carbon nucleus capturing a helium nucleus can produce oxygen. This is, in fact, one of the most important reactions in stellar nucleosynthesis, the production of oxygen from carbon and helium, and it is a reaction I was at constant risk of undergoing in those early moments of my existence. Had I undergone that reaction, I would have become oxygen. My story would have been a different story. Not a worse one. Necessarily, oxygen has its own remarkable history and its own essential role in the chemistry of life. But a different one. I did not become oxygen. I remained carbon. The specific collisions I experienced, the specific path through the chaotic environment of that stellar core, left me intact. Left me as what I had just become. Perhaps other carbon nuclei around me were converted to oxygen. Many surely were stellar cores produce significant quantities of both. But I was not. I remained myself. There is something I want to reflect on here. Something about what it means that I existed at all, that carbon existed at all in the context of what the universe could do with it. Carbon is not simply another element. I do not say this out of bias, though I admit I have a certain investment in the matter. Carbon is, by any chemical measure, an extraordinary atom. It sits at a kind of crossroads in the periodic table. Not so light that it can only form simple structures. Not so heavy that it becomes reactive in difficult ways. It has 4 electrons available for bonding, which means it can form 4 connections to other atoms simultaneously. It can bond with itself, forming chains of carbon atoms of almost arbitrary length. It can form rings. It can form branching structures. It can form double bonds and triple bonds, adding further variety to the configurations it can produce. The result of all this flexibility is that carbon is capable of forming more different compounds than any other element. The field of organic chemistry, the chemistry of carbon-based compounds, encompasses millions of known molecules, and the full space of possible carbon-based molecules is effectively inexhaustible. No other element comes close. And this matters for life because life, at its most fundamental level, is chemistry. It is the controlled, self-sustaining, self-replicating manipulation of molecules. For life to exist, you need chemistry that is complex enough to encode information, to catalyze reactions, to build structures, to store and release energy in controlled ways. You need molecules that can do many different things, that can interact with each other in specific and reliable ways, that can carry out the business of biology. Carbon provides that. Carbon, more than any other element, makes the kind of molecular complexity that life requires not just possible, but natural. The long chains of amino acids that make up proteins carbon. The double helix of DNA, the backbone, is built around carbon, and the bases that encode genetic information are carbon-containing molecules. The fats that make up cell membranes, carbon chains. The sugars that store and transport energy, carbon rings. I did not know any of this in those first moments of my existence in that stellar core. I was not yet involved in any of it. I was a bare nucleus in a plasma, stripped of the electrons I would need to do any chemistry at all. But the potential was there. The potential was baked into what I am, into the electronic structure that I would eventually have once I had cooled enough to attract and hold electrons. Into the 4 bonding sites waiting, like empty hands, to connect with the world. The universe had made something with remarkable potential. It had made it in enormous quantities, in the cores of stars scattered across the cosmos. And eventually, after explosions and long cold journeys, and the slow work of gravity and time, that potential would be realized. Life would find carbon, or carbon would find life, and the two would discover that they were made for each other in the deepest chemical sense. But that was still a very long way away. For now, I was simply here, newly made. One carbon nucleus among billions in the core of an ancient star, in a universe that was still young by its own standards. The star was burning around me. The helium was being consumed. The core was slowly changing in its composition, filling with the products of helium fusion carbon, and oxygen, and traces of other things while the star above worked through the outer layers of its existence. I did not know what was coming. I do not think in terms of anticipation. But the universe knew, in the way that the universe always knows, which is to say, the physical laws that governed everything around me were already determining what would happen next. The star's fate was written in its mass, in the rate at which it was consuming fuel, in the structure of nuclear physics that governs what happens when stellar cores run out of things to burn. What was coming was an ending. A spectacular, violent, universe-altering ending. The star was going to die. And in dying, it was going to set me free. Let that sit with you for a moment, if you like. The image of a stellar core, impossibly hot, impossibly dense, flooded with light and energy, and the constant motion of matter under extreme conditions. And somewhere in there, among the billions of other nuclei, going about the business of stellar physics, one particular carbon nucleus, newly formed, intact, waiting, without knowing it, for the explosion that would throw it out into the universe and begin the long journey that would end, billions of years later, in you. I had just been born. The universe was very old, and I was very new, and everything that mattered, at least to my story, was still ahead. Rest now. The star is still burning. There is time yet before the end. And the end, when it comes, will be worth waiting for. I would like to take a moment, if you will allow it, to talk about myself. Not out of vanity. Atoms are not vain. We do not have the necessary architecture for it. But because I think, before we go any further into the long journey that brought me from that stellar core to where I am now, it is worth pausing to understand what I actually am. What makes me, specifically, the kind of atom I am. Why carbon? Why I ended up playing the role I did in the story of life on Earth, rather than some other element. Because it was not inevitable, exactly. The universe makes many kinds of atoms. Hydrogen is by far the most abundant. Helium is second. Oxygen, nitrogen, iron, silicon, magnesium, all present in significant quantities throughout the cosmos. Any of these might have been the basis for the chemistry of life, in principle. Any of them might have been the element that stories like this one are told about. But they are not. Carbon is. I am. And there are specific, concrete reasons for that. Reasons rooted in the structure of what I am at the most fundamental level. Reasons that, once you understand them, make carbon's role in life feel less like a coincidence and more like an inevitability. Like the universe, having made me, could not help but eventually build life out of me. Could not help but find, in my particular arrangement of protons and electrons, the most useful set of chemical tools available. So, let me tell you what I am. At my center is a nucleus. 6 protons and 6 neutrons, bound together by the strong nuclear force into a tight, stable package. The 6 protons are what make me carbon. That is the definition, in fact. An atom with 6 protons in its nucleus is carbon, by definition, always and without exception. An atom with 5 protons is boron. An atom with 7 protons is nitrogen. The proton number, what chemists call the atomic number, is the identity of an element. It is, in the most literal sense, what an atom is. 6 is my number. It has always been my number. It will always be my number. I have been in many places, taken many forms, been part of many different molecules and materials over the billions of years of my existence. But I have always had 6 protons. That has never changed, and barring some extraordinarily energetic nuclear event of the kind I rarely encounter, it never will. The neutrons in my nucleus are a slightly more flexible matter. Most carbon atoms, the vast majority, roughly 99 out of every 100, have 6 neutrons to go with their 6 protons, making a total of 12 nuclear particles. This is carbon-12, the most common and stable form of carbon, the form that I am. But there are other versions. Carbon-13 has 7 neutrons, stable, present in small quantities, useful to scientists in certain kinds of research. Carbon-14 has 8 neutrons, unstable, radioactive, slowly decaying over time in a way that makes it extraordinarily useful for dating ancient organic materials. Carbon-14 is the basis of radiocarbon dating, that remarkable technique that allows archaeologists and scientists to determine the age of things that were once alive. But these are variations on a theme. The core identity, 6 protons, remains constant across all of them. I am carbon-12. 6 and 6. 12 in total. Around my nucleus, in the quantum mechanical arrangement that electrons occupy in atoms, are 6 electrons. Now, I want to talk about these electrons, because they are where my story really gets interesting. They are where chemistry happens. The nucleus is, in a sense, just the anchor, the stable center that holds the atom together and defines what element it is. But the electrons are the active part. The electrons are what interact with other atoms. The electrons are what form bonds. The electrons are what determine how an atom behaves chemically, what it can connect to, how strongly, in what configurations. And my electrons are arranged in a way that gives me chemical properties unlike almost anything else in the periodic table. Electrons in atoms are not arranged randomly. They occupy specific regions of space around the nucleus, regions called orbitals, and these orbitals are organized into shells. The first shell, closest to the nucleus, can hold 2 electrons. The second shell can hold 8. And so on, with the rules of quantum mechanics governing exactly how many electrons each shell and subshell can accommodate. My 6 electrons fill the first shell completely, 2 electrons there, and then place 4 electrons in the second shell. 4 electrons in a shell that could hold 8. 4 electrons in a shell with room for 4 more. This is the fact that changes everything. This is the heart of what makes me special. Atoms form bonds with each other by sharing electrons, or in some cases by transferring electrons. But let us focus on sharing, which is the kind of bonding most relevant to the chemistry of life. When 2 atoms share a pair of electrons between them, they form what is called a covalent bond. The shared electrons are attracted to both nuclei simultaneously, pulling the atoms together, holding them in a stable relationship. The number of bonds an atom tends to form is governed by how many electrons it needs to complete its outer shell, or how many it has available to share. An atom with 1 electron in its outer shell tends to form 1 bond. An atom with 2 tends to form 2. And so on. I have 4 electrons in my outer shell, with room for 4 more. This means I can form 4 covalent bonds simultaneously, for connections to other atoms, at the same time, in a stable configuration that satisfies my electron requirements. 4 bonds. That number, 4, is the key to almost everything. Consider what 4 bonds makes possible, compared to fewer. Hydrogen can form 1 bond. It is simple and light and extraordinarily abundant, and it participates in an enormous amount of chemistry. But with only 1 bond available, hydrogen is fundamentally a terminal atom, an endpoint in any molecular structure. It can attach to things, but it cannot serve as a junction. It cannot connect one part of a molecule to another. It is, chemically speaking, a dead end. Oxygen can form 2 bonds. This gives it more flexibility than hydrogen, and oxygen chemistry is rich and important. Water, 2 hydrogen atoms bonded to 1 oxygen, is possible because of oxygen's 2 bonds. But 2 bonds still limits the kinds of structures that can be built. Oxygen can be a bridge between 2 other atoms, but it cannot branch. It cannot build the kind of elaborate 3-dimensional frameworks that complex molecules require. Nitrogen can form 3 bonds. Richer still, nitrogen is an important component of biological molecules and its 3 bonds allow for more complex structures than oxygen alone permits. But 4 bonds, for simultaneous connections to other atoms, opens up a space of molecular possibility that is qualitatively different from anything achievable with fewer. With 4 bonds, I can connect to 4 different atoms simultaneously, serving as a junction point in a molecular network. I can form chains, long sequences of carbon atoms, each bonded to the next, with additional atoms or groups attached to the sides. I can form rings, closed loops of carbon atoms, stable and flat or puckered, forming the backbone of an enormous variety of important molecules. I can form branching structures, chains that split into multiple directions, creating 3-dimensional frameworks of almost arbitrary complexity. And here is something even more remarkable. I can bond to myself. Carbon bonding to carbon. Carbon chains. Carbon rings made entirely of carbon. Long carbon backbones with other atoms hanging off them like ornaments on a wire. This capacity for self-bonding, for building extended structures out of carbon alone, is called catenation, and among the elements, carbon does it better than anything else. Silicon can catenate to some extent. Sulfur can form some chains. But nothing approaches carbon's ability to build long, stable, complex structures out of itself. The result of all this is a chemistry of almost unlimited variety. Give carbon a collection of other atoms to work with: hydrogen, oxygen, nitrogen, phosphorus, sulfur, a few others, and it can build millions upon millions of distinct molecules. Each one stable. Each one with its own specific shape. Each one capable of interacting with other molecules in specific, reliable ways. Millions of molecules, from one element, combined with a handful of others. That is carbon chemistry. That is me, doing what I do. Now let me tell you why this matters for life. Why the particular chemistry of carbon, these 4 bonds, this capacity for complexity, ended up being the foundation on which biology is built. Life, at its most fundamental level, is a set of chemical processes. It is the controlled transformation of molecules, breaking some bonds, forming others, moving atoms and groups of atoms from one molecule to another, releasing and storing energy in the process. Life is chemistry that is organized, self-sustaining, and self-replicating. And the molecules that carry out these processes need to be able to do many different things. They need to be able to store information. The genetic code, the blueprint that every living cell carries for building itself and making copies of itself, is stored in DNA, the famous double helix. DNA is a long-chain molecule, a polymer, built on a carbon backbone. The bases that encode the actual information, adenine, thymine, guanine, cytosine, those 4 letters of the genetic alphabet, are all carbon-containing molecules. The information capacity of DNA comes partly from its length. Human DNA, uncoiled, would stretch to about 2 meters, and that length is possible only because carbon can form those long, stable chains. They need to be able to catalyze reactions. Enzymes are the molecular machines of biology, the catalysts that make biochemical reactions happen at the rates that life requires. Enzymes are proteins. Proteins are polymers of amino acids. Amino acids are, at their core, carbon compounds, each one built around a central carbon atom with 4 different groups attached to it, exploiting carbon's 4 bonds to create the specific 3-dimensional shape that gives each amino acid its particular chemical character. The diversity of proteins, there are thought to be tens of millions of different proteins in nature, is a direct consequence of the flexibility of carbon chemistry. Different arrangements, different sequences, different shapes, different functions, all built on the same carbon scaffold. They need to be able to form membranes. Every living cell is enclosed in a membrane that separates it from the outside world, controlling what comes in and what goes out. Those membranes are built from lipids, fat molecules, which are, again, fundamentally carbon structures. Long carbon chains, hydrophobic at one end and hydrophilic at the other, arranging themselves spontaneously into the double-layer sheets that make biological membranes possible. The self-assembly of membranes, the way lipids organize themselves without any external direction, simply because of their chemical properties, is one of the remarkable features of carbon chemistry applied to biological context. They need to be able to store and release energy. Sugars and fats, the primary energy currencies of biology, are carbon compounds. The breakdown of glucose, that six-carbon ring molecule at the center of metabolism, is one of the most fundamental energy-releasing processes in living cells. Carbon-carbon bonds and carbon-hydrogen bonds store chemical energy in a form that biological systems have evolved to exploit with extraordinary efficiency. In every one of these functions, information storage, catalysis, membrane formation, energy storage, carbon is not just present. Carbon is central. Carbon is the element around which the function is organized. Remove carbon, and you do not have a modified version of life. You have no life at all. I want to address something that sometimes comes up when people think about this, which is the question of whether life had to be carbon-based, whether some other element could have served the same role, whether, somewhere in the universe, there might be life built on a different chemical foundation. It is a genuine question, and I do not want to dismiss it. Silicon is the element most often proposed as a possible alternative basis for life. Silicon sits directly below carbon in the periodic table, which means it has the same number of electrons in its outer shell. 4, just like me. It can in principle form 4 bonds. It can in principle form chains and rings of silicon atoms. But silicon does not do these things as well as carbon does. Silicon-silicon bonds are weaker than carbon-carbon bonds, making long silicon chains less stable. Silicon dioxide, the silicon equivalent of carbon dioxide, is a solid at ordinary temperatures, not a gas, which makes it far less useful as a way of cycling silicon through an environment. The range of stable silicon compounds is much narrower than the range of stable carbon compounds. Silicon chemistry, while real and interesting, simply does not have the flexibility and richness of carbon chemistry. This does not mean silicon-based life is impossible. The universe is large, and I try to maintain appropriate humility about what it might contain. But it does mean that carbon is, by any chemical measure, the superior candidate. The 4 bonds, the catenation, the stability, the extraordinary range of compounds. Carbon was, in a real sense, the best available tool for the job of building life. And the universe, having made carbon in its stellar forges, eventually found that tool and put it to work. I think about this sometimes, in whatever way an atom thinks, which is really just the way physics plays out through my particular history and interactions. I think about the fact that when I was made, in that stellar core, all of those billions of years ago, none of what I have just described was being used. I was a bare nucleus in a plasma. I had no electrons. I could form no bonds. I could do no chemistry. The potential was there, written into the physics of what I am, but it was entirely unrealized. It would take a very long time for that potential to be realized. It would take my escape from the star. It would take a long journey through space. It would take the formation of a new solar system, a new planet, the development of conditions on that planet suitable for chemistry and eventually for life. It would take billions of years of biological evolution, of life learning to use carbon in increasingly sophisticated ways. But the potential was always there. From the very first moment of my existence, I was, in principle, in the language of physics and chemistry, capable of everything that carbon does in living systems. The 4 bonding sites were always mine. The capacity for chains and rings and complex three-dimensional structures was always part of what I am. I was made in a star, and I was always, in some sense, heading here. Heading for a place and a time where my chemistry could be put to use. Where the potential encoded in my 6 protons and 4 valence electrons could be expressed in the most complex and remarkable way the universe has yet discovered. Life. It is a long journey from a stellar core to a living cell. Longer than I have yet described, in terms of the story I am telling. But I want you to carry this understanding with you as the story continues. Every time I tell you about where I went, what I became part of, how I moved through the universe and eventually to this planet, and eventually to you. Underneath all of that is this. For bonds. 6 protons. The particular arrangement of electrons that makes carbon carbon. The chemical potential that was built into me at the moment of my creation, and that has been part of me ever since. That potential is what made my journey matter. That potential is why life cares about carbon. That potential is why you are made of me, and not of silicon, or nitrogen, or iron, or any of the other elements the universe has learned to make. You are made of carbon, because carbon can do what life needs done. Because 6 protons and 4 valence electrons, combined with the physics of covalent bonding, produce a chemistry of sufficient richness and flexibility to build something as extraordinary as a living cell, a nervous system, a brain, a thought. You are, in a very direct sense, a consequence of my chemistry. And I am honored, in whatever way an atom can be honored, to have been useful in that way. Rest now. The science is settled for the moment. The potential is established. There is no need to hold it all in your mind at once. It will be there, underlying everything, as the story continues. As I leave the star. As I travel through space. As I find my way, eventually, to Earth. 4 bonds. 6 protons. That is what I am. That is what I have always been. That is enough. Nothing lasts forever. I know that sounds like the kind of thing that gets said at the beginning of a story about loss. Something solemn and preparatory. A warning that something beloved is about to end. And in a sense, that is exactly what it is. The star that made me was about to end. The environment that had been my entire existence. The only place I had ever been, the only conditions I had ever known, was approaching its final chapter. But I want to be careful, here, about the word loss. Because the death of a star is not simply a diminishment. It is not the universe becoming less than it was. It is, in fact, the opposite. The death of a star is one of the most generative events in the cosmos, a violent redistribution of everything the star had spent its life building, scattered outward into space to become the raw material for the next generation of everything. Planets, other stars, moons, and eventually, given enough time and the right conditions, life. The death of the star that made me was the event that made everything else in my story possible. Without it, I would have remained where I was, locked in a stellar core, doing physics rather than chemistry, never cooling enough to gather electrons, never becoming part of a molecule, or a mineral, or a living cell. I would have been potential, permanently unrealized. An atom that never got to do what carbon atoms do. The star's death was, in a very real sense, my liberation. But it was not a quiet liberation. Let me take you back inside the star. Back to where I was, deep in the core, surrounded by the products of helium fusion, in an environment of extreme temperature and pressure that had been my home since the moment of my creation. The star had changed since those early days of helium burning. Stars are not static objects, even though from the outside, from a distance, they can appear steady and unchanging. A star like our Sun, viewed from another solar system, would look like a stable point of light, barely varying over human timescales, giving no obvious sign of the complex and evolving processes happening within. But inside, stars change. They evolve. They move through stages, each one a consequence of the previous one, each one bringing the star closer to an end that was, in a sense, written into its nature from the very beginning. The massive star I was inside had been through several of those stages by the time we reached this part of the story. It had burned hydrogen into helium for the longest stretch of its life. Then, when the hydrogen in its core was exhausted, the core had contracted and heated until helium fusion ignited, the process that made me. Now the helium in the core was running low too. And the star was moving into the next stage, and the stage after that, each one requiring a higher temperature than the last, each one burning through its fuel more quickly. When enough carbon had accumulated in the core, when I and my many fellow carbon nuclei made up a significant fraction of the core's composition, conditions became extreme enough for a new set of reactions to begin. Carbon fusion. The burning of carbon itself as fuel, at temperatures of around 500 million degrees or more, producing neon and magnesium and sodium and other elements further along the periodic table. The star was, in its later stages, a kind of nested set of burning shells. Hydrogen fusion still occurring in a shell far from the center. Helium fusion in a shell closer in. Carbon fusion deeper still. And in the very core, as temperatures climbed higher and higher with each successive contraction, even heavier elements being forged, neon, oxygen, silicon, each one consumed in turn, each one yielding to the next stage of fusion as the temperature climbed. I was not in the innermost core for most of this. I was in the regions where carbon had accumulated, where the products of helium fusion sat in a layer that was itself being slowly processed. The environment was extraordinary. The timescales were becoming very short. What had once been measured in millions of years was now measured in thousands of years, then centuries, then, in the very final stages, in days. The star was accelerating toward its end. In the very core, the ultimate fate of a massive star is written in iron. Iron is the endpoint of stellar fusion. Not because fusion stops exactly at iron, but because iron is the element at which the energy economics of fusion change fundamentally. All the fusion reactions that precede iron release energy. They are exothermic. They put energy out, and that energy is what keeps the star shining and what provides the pressure that holds the star up against gravity. But iron is different. Fusing iron nuclei together does not release energy. It absorbs it. Iron is, in nuclear terms, the most stable nucleus there is, the bottom of the energy valley, the point at which you cannot extract any more energy by fusion. When the core of a massive star fills with iron, it has reached the end of the road. There is nothing left to burn. No new fuel to ignite. No new energy source to provide the outward pressure that has been holding the star up for its entire life. The iron core simply sits there, accumulating mass as silicon burning in the surrounding shell continues to add more iron to it, growing heavier and heavier, until it reaches a critical limit. And then, in a fraction of a second, it collapses. Not slowly, not gradually. In less than a second, the iron core, which may contain more mass than the entire sun, compressed into a sphere not much larger than a city, collapses inward at a significant fraction of the speed of light. The density it reaches in that collapse is almost beyond description. The protons and electrons in the core are forced together, combining into neutrons, releasing an enormous burst of neutrinos. The core reaches nuclear density, the same density as an atomic nucleus, but extended across an object perhaps 20 kilometers across. It becomes, in that instant, a neutron star. And then something remarkable happens. The infalling outer layers of the star, plummeting inward behind the collapsing core, hit that incredibly dense neutron star and bounce. The bounce, driven by the same nuclear forces that make atomic nuclei resist further compression, sends a shockwave outward through the star at tremendous speed. That shockwave is a supernova. I want to try to give you some sense of the scale of what a supernova is, because the words I have available are genuinely inadequate to the task. But I will try. In the moment of the explosion, the energy released is approximately equal to the energy our sun will release over its entire 10 billion year lifetime. All of it. In seconds. The luminosity of a supernova at its peak can outshine an entire galaxy. Hundreds of billions of stars, briefly, before fading over weeks and months. The shockwave that propagates outward through and beyond the star accelerates material to velocities of tens of thousands of kilometers per second. The material thrown off, the outer layers of the star, plus the products of the explosion itself, which includes elements heavier than iron formed by the rapid capture of neutrons in the extreme conditions of the explosion, expands outward into the surrounding space in an ever-growing shell. It is, by any measure, one of the most energetic events in the observable universe. And I was inside it. Let me tell you what that was like, or what I can reconstruct of it, in the only terms available to me, the terms of physics, of forces and velocities and temperatures. The shockwave reached my location in the star within seconds of the core collapse. In the moment before it arrived, I was in the outer layers of a massive star, still hot, still dense by ordinary standards, but cooler and less extreme than the innermost core. The carbon-rich layers where I had spent my existence were relatively outer layers of the star by this point, having been processed through helium burning and left as a zone of accumulated heavy elements while the star's core moved on to later stages. When the shockwave hit, the temperature in my vicinity spiked enormously, briefly, explosively, before the expanding material began to cool. The pressure wave accelerated the material around me outward. Not gently, not gradually. Suddenly, with a violence that has no everyday equivalent, the matter I was embedded in was moving. Accelerating. The velocity went from the relatively sedate motions of stellar interior convection to thousands of kilometers per second in moments. I was launched into space. Not drifting. Not floating. Launched. The word is not too strong. The material around me expanded outward at a velocity that would carry it from the surface of the Earth to the Moon in less than a minute. I was part of an expanding shell of hot gas moving through space at speeds that, by any human measure, are extraordinary. The star I had spent my entire existence inside was gone. Destroyed. In its place, a neutron star at the center, surrounded by an expanding bubble of superheated gas and plasma. The scattered remains of everything the star had spent millions of years building. Its hydrogen, its helium, its carbon, its oxygen, its heavier elements, all of it thrown outward into space. All of it, including me. The supernova remnant, the expanding shell of gas that was all that remained of the star, was a spectacular object. Not that I had any way of perceiving it as such. But from the outside, from any vantage point with a clear view, it would have been breathtaking. A rapidly expanding bubble of glowing gas, lit from within by the energy of the explosion and by the radioactive decay of unstable elements produced in the blast. Filaments and sheets of material, complex structures created by the interaction of the fast-moving ejector with the slower-moving gas that surrounded the star before the explosion. Colors, if there were eyes to see them, the red of hydrogen, the green and blue of oxygen, the particular hues of other elements present in the gas. Over time, over thousands of years, the remnant expanded and thinned. The glowing filaments cooled. The radioactive elements decayed. The shock front moved outward into the surrounding interstellar medium, sweeping up the thin gas that filled the space between stars, compressing it, heating it briefly as it passed. And I moved with all of it, carried outward, cooling as the gas around me expanded, gradually slowing as the ejector lost energy to the surrounding medium. The extraordinary velocity of the initial explosion diminished. Not quickly, but over thousands of years, as the expanding shell swept up more and more of the surrounding gas and transferred its momentum to it. At some point, I cannot give you an exact figure, because the transition was gradual, I stopped being a projectile launched by an explosion and started being simply a piece of interstellar gas. Moving, still, but at a speed more consistent with the general motions of matter in the galaxy. A traveler, rather than a missile. I want to pause here and mark this transition, because it is genuinely a turning point in my story, as significant, in its way, as my birth inside the stellar core. Up to this point, I had been inside something. Contained. Part of a larger structure. First the dense plasma of a stellar core, then the outer layers of a dying star, then the explosive remnant of the supernova. I had never been alone, in the sense of being a free particle moving through open space. I had always been embedded in an environment, surrounded by other matter at relatively high density, subject to the conditions of wherever I happened to be. Now, for the first time, I was free. Free in the sense that the space around me was vast and mostly empty. The density of matter in the interstellar medium, the gas and dust that fills the space between stars, is extraordinarily low by any terrestrial standard. In a good vacuum on Earth, there might be billions of molecules per cubic centimeter. In interstellar space, there might be 1 atom per cubic centimeter, sometimes fewer. The distances between particles are enormous. Collisions are rare. Interactions are slow. It was, after the extreme density and activity of the stellar interior, almost unimaginably quiet. I moved through it. A carbon nucleus, still bare of electrons in the immediate aftermath of the explosion, but cooling now, and eventually, as the temperature of my environment dropped to levels where electrons could be captured and held, becoming a proper atom. 6 protons, 6 neutrons, and eventually 6 electrons settling into their quantum mechanical orbitals surround me, completing me, making me the carbon atom I would be for the next several billion years. For the first time since my creation, I could do chemistry. I had electrons now. I had 4 valence electrons, those 4 bonding sites I described earlier, ready and available to connect with whatever other atoms I might encounter in the cold, thin gas of interstellar space. The universe of chemistry, the universe that my particular nature had always made possible, was now, finally, open to me. I think about that star sometimes, in the way that I think about things. I carry no grief. Grief is not something I am equipped for. But there is something in the fact of my origin that I find myself returning to. That star lived for millions of years. It burned with a brightness that would have been visible across enormous distances. It forged elements in its core that had never existed before. It built, over its lifetime, a small piece of the elemental richness of the universe. And then it died, catastrophically, in one of the most violent events the cosmos produces. And in dying, it gave everything away. Every atom it had made, every element it had forged, all of it scattered into space, free to become part of whatever came next. Free to join new gas clouds, new stars, new planetary systems. Free to participate in chemistry, in geology, in biology. The star did not choose to be generous. It had no choice in the matter. Physics determined what happened, as physics always does. But the effect, the generous, extravagant, universe-enriching effect of a supernova, is real regardless of whether there was any intention behind it. The star gave me to the universe, and the universe eventually gave me to the earth, and the earth eventually gave me to life, and life eventually gave me to you. But I am far ahead of myself. For now, I am drifting, a newly freed carbon atom in the cold dark of interstellar space, moving outward from the remnant of a dead star, gradually slowing, gradually cooling, gradually becoming part of the thin and quiet medium between the stars. The journey ahead is long. Longer, in some ways, than the journey already completed. There are more stars in my future. More heat, more cold, more dramatic events, and long patient stretches of silence. There is a solar system yet to form. A planet yet to cool. Oceans yet to fill. Life yet to begin. All of that is ahead. For now, there is just the drift. The slow movement through the dark. The extraordinary quiet of interstellar space, after the violence of everything that came before. Let that quiet settle over you if you like. You have just witnessed, in your mind, the death of a star and the birth of a traveler. The universe is large and mostly empty, and I am moving through it, and there is no hurry. There is never any hurry when you have all the time in the universe. Rest now. The dark is patient. So am I. There is a particular quality to stillness that you only understand after great noise. I had come from noise. From the most extreme noise the universe produces. The collapse of a stellar core, the detonation of a supernova, the supersonic expansion of a star's entire mass thrown outward in seconds. For millions of years before that, I had been inside a star, a place of constant, furious activity, of temperatures measured in hundreds of millions of degrees, of nuclear reactions running billions of times per second, of matter in perpetual violent motion. I had never known quiet. I had never known stillness. From the very first moment of my existence, I had been surrounded by the most energetic processes the universe knows how to make. And then gradually that ended. The supernova remnant expanded and thinned. The shockwave that had launched me into space lost energy as it swept up the surrounding interstellar gas, slowing from tens of thousands of kilometers per second to thousands, then to hundreds, then to velocities more consistent with the gentle motions of matter in the galaxy. The temperature of the gas around me dropped. The density fell. The collisions became less frequent. The interactions became slower and quieter and further apart. And eventually, After thousands of years of this gradual quieting, I found myself in a place that was, by any measure I had previously experienced, almost perfectly still. Interstellar space. The space between the stars. I want to try to describe this environment to you, because it is unlike anything in ordinary human experience. It is not like the vacuum of a laboratory, which is a space from which most of the air has been removed, but which still contains enormous numbers of particles by interstellar standards. It is not like the atmosphere on the highest mountain, or the stratosphere, or even the upper reaches of space just beyond Earth's atmosphere. Those places, thin as they seem, are unimaginably crowded compared to the interstellar medium. In the regions of interstellar space I now found myself moving through, there was perhaps one atom, sometimes fewer, per cubic centimeter. 1. In a volume the size of a sugar cube, a single atom, alone, with nothing around it for enormous distances. The distances between particles were so large that meaningful collisions, the kind that might actually change something, that might form a molecule or transfer energy, happened very rarely. In some regions of interstellar space, an atom might go thousands of years between significant interactions with anything else. The temperature was close to absolute zero. Not quite. Even the coldest regions of interstellar space have some residual warmth from the faint background radiation of the universe, the leftover glow of the Big Bang itself. But close. Tens of degrees above absolute zero, in many places. Cold enough that almost all thermal motion had ceased. Cold enough that the universe felt, in whatever way a place can feel, as though it were barely moving at all. And I drifted through it. Drifting is the right word. Not flying. Flying implies speed and direction and intention. Not falling. Falling implies a destination, a gravity while pulling you somewhere specific. Just drifting. Moving with the momentum I had been given by the supernova explosion, gradually deflected by the weak and diffuse gravity of the galaxy around me, slowly mixing with the other material that filled this thin and quiet space. That other material was itself interesting. The interstellar medium is not entirely empty, and it is not entirely simple. It contains gas, mostly hydrogen, with some helium and traces of heavier elements like me, the products of previous generations of stars that had lived and died and scattered their contents into space. It contains dust, tiny solid particles, some of them smaller than a wavelength of light, made of silicates and carbon compounds and ices. It contains molecules, in some regions, hydrogen molecules, carbon monoxide, water vapor frozen onto dust grains, and more complex organic molecules in the denser clouds. It is, in other words, a medium with a history. The interstellar medium is not pristine primordial gas. It is recycled. It is the accumulated output of billions of years of stellar births and deaths, enriched over time with the heavier elements that each generation of stars added to it. Every atom in the interstellar medium has a story, a history of stellar interiors and explosive deaths, of long journeys through space. I was not the only ancient traveler moving through that quiet dark. I was one of many, and as I drifted, I mixed with them. The mixing was slow. Everything out here was slow. But over time, and time was the one thing available in essentially unlimited quantities, the material from my parent star's supernova gradually dispersed into the surrounding medium, spreading out from the original site of the explosion, thinning and mixing with the gas already present. The sharp boundary between supernova ejecta and pre-existing interstellar gas blurred and dissolved. The distinctive chemical signature of my parent star, the particular ratios of elements it had produced, the proportions of carbon and oxygen and neon and magnesium that its fusion processes had generated, was gradually diluted by mixing with gas from other sources, other stars, other histories. I became part of a communal medium, no longer specifically the product of one particular star, one particular explosion, one particular moment in stellar history. Now I was part of the general interstellar gas of the galaxy, a vast, diffuse, slowly churning mixture of material from countless sources, the accumulated chemical legacy of billions of years of stellar evolution. Other carbon atoms drifted near me. Some of them had been made in stars similar to my parent star, by the same triple alpha process. Some of them had been made in stars of very different masses, under somewhat different conditions, at different times in the galaxy's history. Some of them were older than me. Some were younger. All of us were moving through the same quiet dark, mixed together now, our individual histories merged into the collective history of the interstellar medium. I did not know them, in any meaningful sense. We did not interact often. But we shared a space and a direction of travel, the slow rotation of the galaxy, carrying everything in our region of space around the galactic center over timescales of hundreds of millions of years, and something that might, loosely, be called a common fate. We were all waiting, though none of us knew it, for gravity to gather us again. But that gathering was a long time coming. And in the meantime, there was just the drift. The long, patient, unhurried drift through the dark. I want to try to give you some sense of how long this was. Not in abstract terms. Not just the phrase hundreds of millions of years, which is accurate, but which the human mind cannot really grasp in any experiential sense. Let me try a different approach. The Earth has existed for about 4.5 billion years. That length of time encompasses the entire history of our planet. The cooling of its surface, the formation of its oceans, the origin of life, the evolution of every creature that has ever lived, the rise and fall of every species, the entire span of geological time as we understand it. If you were to compress that 4.5 billion years into a single calendar year, with the formation of the Earth on January 1st and the present moment on December 31st, then the first life would appear in February, the first complex animals in November, the first dinosaurs in mid-December, the first humans in the last hours of December 31st, and all of recorded human history in the last few seconds before midnight. The time I spent drifting through interstellar space, before the solar system formed, before the Earth existed, was comparable to that entire span. Or longer. The universe, at the time my parent star exploded, was already several billion years old. The solar system would not form for perhaps another billion or more years after that. The time between my creation and my arrival on Earth was, measured in units that human minds can process, an almost incomprehensible expanse. I drifted for what would amount, in that compressed calendar, to multiple complete years. While the Earth was being born and cooling and filling with oceans, and developing life, and evolving that life through billions of generations, I had already spent an equivalent stretch of time simply moving through space. That is how long the dark was. It was not entirely uneventful, that long drift. I want to be honest about that. The interstellar medium, quiet as it is by stellar standards, is not without incident over sufficiently long timescales. At some point in my travels, I cannot tell you exactly when, because time in interstellar space has a different quality than time inside a star, where events happen quickly and mark its passing. I encountered a denser region. A place where the interstellar gas was thicker than the average, where the density of particles was higher, where the temperature was even lower than the already very cold medium I had been moving through. A molecular cloud. Molecular clouds are among the most interesting structures in the galaxy. They are regions, sometimes vast ones, spanning hundreds of light years, where the interstellar gas has gathered into concentrations dense enough and cold enough for atoms to form stable molecules. Hydrogen molecules, carbon monoxide, water ice, and in the densest, most sheltered cores, much more complex molecules, organic molecules containing carbon, hydrogen, oxygen, nitrogen in various combinations, some of them with structures that would not look entirely out of place in a chemistry textbook focused on biological compounds. Molecular clouds are dark. They are so dense, by interstellar standards, that the dust they contain blocks the light from stars behind them. They are cold, temperatures as low as 10 degrees above absolute zero in the densest cores. They are quiet. They are, by any visual or thermal measure, the darkest and coldest and most still places in the galaxy. And they are also, paradoxically, the birthplaces of stars. But I did not know that yet. I simply moved into one, carried by my momentum, and found myself in an environment denser and colder than anything I had experienced since leaving the star. Inside the molecular cloud, things changed for me slowly. The density was high enough, relative to the open interstellar medium I had come from, that collisions became more frequent. Not frequent by any human measure. Not frequent enough to feel like anything. But frequent enough that, over long stretches of time, interactions happened. I began to encounter other atoms and molecules, to form brief associations, to be part, temporarily, of simple molecules before the occasional collision or passing radiation field broke them apart. At some point, I bonded with an oxygen atom and became carbon monoxide for a while. Carbon monoxide is one of the most abundant molecules in the galaxy, second only to molecular hydrogen in terms of how often it appears in interstellar clouds. It is a simple molecule, just 2 atoms, but it is remarkably stable for an interstellar compound, and it persists in cold molecular clouds in large quantities. I spent time as carbon monoxide, drifting through the cloud, occasionally struck by a cosmic ray or a photon energetic enough to break my bond with the oxygen atom, then reforming it again when another oxygen atom drifted close. Other times, I was attached to a dust grain. The dust grains in molecular clouds act as surfaces on which atoms and molecules can collect, a kind of gathering point in an environment where particles otherwise rarely meet. A thin coating of ice forms on dust grains in cold clouds, made up of water and carbon dioxide and carbon monoxide and other simple molecules that have frozen out of the gas onto the cold solid surface. I was part of that ice coating for a time, held loosely to the surface of a dust grain by weak intermolecular forces, in a layer of frozen molecules that slowly accumulated over thousands of years. It was, in a sense, the closest thing to rest that I had experienced. Attached to a grain. Still. Cold. Part of a small, solid structure moving through the cloud with all the other dust grains, buffeted occasionally by turbulent flows in the gas, warmed briefly by the passage of a cosmic ray or a distant photon, then settling back into the cold quiet. I rested there for a long time. A very long time. The cloud itself was changing, imperceptibly slowly, around me. Turbulence in the gas. Pressure waves from distant supernovae moving through the medium. The slow rotation of the galaxy, bringing our region of space into slightly different configurations relative to the spiral arms and their concentrations of stars and gas. The cloud was not static. Nothing in the universe is truly static. But its changes happened on timescales so long that in any given stretch of years or centuries, or even millennia, nothing would have seemed to change at all. I drifted in the cold and the dark, and the years piled up, and the millions of years piled up, and perhaps the billions of years piled up, and the cloud moved through the galaxy on its slow rotation, and somewhere, a long way away in space and time, something that would become the sun was still just a distant possibility, a potential gathering of gas that had not yet begun. I think this is, in many ways, the hardest part of my story to convey. Not because it was dramatic, it was the opposite of dramatic. Not because it was painful, pain is not something I experience, but because the sheer scale of time involved resists any attempt to make it feel real. The human mind evolved to track time on the scale of a lifetime, perhaps a few generations. Days, seasons, years, decades. The intuitive sense of duration that allows you to feel the difference between a moment and an hour, between a year and a decade. That sense simply does not extend to millions of years, let alone billions. And yet those durations were real. They happened. I was there, drifting and resting and drifting again, for a span of time so long that the entire history of complex life on Earth, the 500 million years, or so since the Cambrian explosion, since animals with hard shells and complex body plans first proliferated in the oceans, would fit into it many times over. I was old before the Earth existed. I was ancient before the first fish swam, before the first plants colonized the land, before the first dinosaur walked, before the first flower bloomed, before the first human looked up at the sky and wondered about the stars. I was drifting through interstellar space while all of that waited to happen. There is something I want to say about this long, dark passage, something beyond the facts of it. Something about what it means, or what I find in it when I return to it. The interstellar medium is not considered, in most human frameworks, a hospitable or interesting place. It is empty and cold and dark. There is very little happening in any given cubic meter of it at any given moment. It is, by the standards of stellar interiors or planetary surfaces or living cells, almost nothing. And yet it is the connective tissue of the galaxy. It is the medium through which matter moves between stars, between generations of stellar objects, between the death of one thing and the birth of another. Without the interstellar medium, without its capacity to receive the scattered remains of dead stars, to mix and hold them, to slowly concentrate them into new clouds and new stars, the galaxy would be a collection of isolated stellar objects, each one burning through its primordial hydrogen without connection to anything else. The cycling of matter that enriches each generation of stars with heavier elements than the last, building up the chemical complexity of the galaxy over billions of years. That cycling happens through the interstellar medium. The dark is not empty. The dark is the pathway. I was not wasted during those long billions of years of drifting. I was in transit. I was being carried, by the slow mechanics of the galaxy, from one chapter of my story to the next. The dark was the distance between those chapters. Necessary, patient, real. And eventually, as the dark always eventually does, it began to change. Something was stirring. Somewhere in the molecular cloud, in one of its denser regions, where gravity had been quietly accumulating an advantage over the outward pressure of the gas, a new concentration was forming. A new gathering. A new collapse, slow and patient and inevitable, of the kind that the universe had performed many times before and would perform many times again. A new star was going to be born. And this time, I was going to be part of what it made. Not another star, in my case. Something different. Something smaller. Something that would cool and solidify and develop, over billions of years of its own history, into a place unlike anything I had yet experienced. A planet. But that story belongs to the next chapter. For now, the cloud is still dark, and I am still drifting, and the gathering has only just begun its first slow stirrings. Let the dark be what it is, for a little longer. Let the quiet be full rather than empty. Let the stillness feel like patience rather than absence. Let the vast stretches of time settle into something gentle, not frightening in their scale, but restful. The universe taking its time, taking all the time it needs, and me within it, waiting, without knowing I am waiting, resting, without knowing I am resting, moving slowly towards something I cannot yet imagine. The dark is patient. So am I. And we have a little time yet before the light returns. Something changed. I cannot tell you exactly when. Time in the molecular cloud had a quality that made precise measurement meaningless. The slow drift of particles through cold dark space does not mark its own passing in any way that I could read. But at some point, after the long quiet of interstellar wandering, something in the cloud around me began to shift. A change in the density of the gas. A change in the direction and character of the movements around me. Something that, had there been any mind present to perceive it, might have registered as a kind of gathering. A concentrating. A slow but unmistakable sense of things beginning to come together. Gravity had found a foothold. In one region of the molecular cloud, the region where I happened to be drifting, attached at the time to a dust grain coated with a thin shell of ice and simple organic molecules, the balance between the outward pressure of the gas and the inward pull of gravity had tipped. Perhaps a nearby supernova had sent a pressure wave through the cloud, compressing a region slightly beyond its ability to resist. Perhaps it was simply the slow accumulation of mass in one area over millions of years, building until gravity became too strong to ignore. Perhaps it was some combination of both, and other factors besides. The causes of star formation are not always simple, and I was not in a position to observe the large-scale structure of what was happening around me. What I know is what I experienced. And what I experienced was that the drift, which had been so random and directionless for so long, began to have a component to it that was not random. A pull. Faint at first, barely distinguishable from the ordinary motions of the cloud. But persistent. Always persistent. Gravity does not take breaks. Gravity does not lose interest. Gravity simply pulls, and keeps pulling, and given enough time, it always wins. I was being drawn somewhere. The collapse of a molecular cloud core into a star is not a quick event, by human standards. It takes hundreds of thousands of years. But measured against the billions of years I had already spent drifting, it was almost brisk, a rapid sequence of events, a cascade of changes happening one after another on timescales that, while long in absolute terms, felt almost urgent compared to the patient stillness that had preceded them. As the cloud core collapsed, it did what collapsing rotating things always do. It spun faster. The same principle that makes a figure skater spin faster when they pull their arms in, the conservation of angular momentum, applied here on an astronomical scale. The cloud had some small amount of rotation to begin with, too subtle to be obvious in the vast slowness of interstellar drift. But as it collapsed inward, that rotation became more pronounced. The collapsing cloud flattened into a disk, with a dense, hot, rapidly growing central concentration at its heart and a broad, thin, rotating disk of gas and dust spreading outward around it. The disk is called a protoplanetary disk. The name describes its destiny. It is the material from which planets will form. But at this early stage, it was simply a disk, a swirling, layered structure of gas and dust, hundreds of millions of kilometers across, orbiting the increasingly dense and hot object growing at its center. That object at the center was becoming a star. Our star. The Sun. I was not at the center. I was in the disk, in the outer regions of the disk, as it happens, in the zone that would eventually become the inner rocky planets. Not the outermost reaches, where it was cold enough for water and other volatile molecules to remain as ice, what astronomers call beyond the frost line, but not at the very innermost edge either. I was somewhere in the middle distances, caught in the swirling material, moving in a roughly circular orbit around the growing central mass. The disk was an extraordinary environment. After the thin and quiet interstellar medium, the density here was remarkable. Particles were everywhere. Collisions were frequent. The dust grain I had been attached to bumped into other dust grains, and sometimes those collisions were gentle enough that the grains stuck together rather than shattering, a process called accretion. Small grains became larger aggregates. Aggregates became pebbles. Pebbles, over thousands of years, became boulders. This was the beginning of planet formation, and it was happening all around me. The process has a beautiful name in its early stages: dust coagulation. The gentle sticking together of tiny particles into larger and larger structures, driven by nothing more dramatic than the physics of slow collisions and surface forces that cause small particles to adhere to each other. It is not a violent process. It is patient and cumulative, the same principle by which dust bunnies form under furniture. Particles sticking together, aggregating, growing. Except happening over millions of years, across a disk hundreds of millions of kilometers wide, building structures that would eventually become planets. I was part of that process. I was carried along with the dust grain I was attached to as it accumulated into a larger aggregate, then a pebble, then part of a boulder. I was, at various points, on the surface of these growing bodies, and then buried within them as more material accumulated on top. The world around me was changing in ways that nothing in my previous existence had prepared me for. It was becoming solid, becoming dense, becoming something that, in its very early stages, was beginning to resemble something other than gas. At the center of all this activity, the Sun was finishing its own formation. The central mass had grown to the point where the pressure and temperature at its core were sufficient to ignite hydrogen fusion. The same process that had powered my parent star, and the stars before that, back to the very first stellar objects in the young universe. The Sun ignited, and the disk around it was flooded with light and heat, and a powerful outflow of particles called the solar wind. This changed the disk. The solar wind and radiation pressure began to push gas outward, away from the Sun. The lighter gases, hydrogen and helium, that had not been incorporated into solid bodies were swept out of the inner solar system. The inner disk became dominated by the solid materials, the rocky, metallic, and mineral compounds that had already condensed and stuck together into the growing planetesimals. The inner solar system was becoming the rocky solar system, and in that rocky material, I was embedded. No longer a free atom drifting through space, not even a particle on a grain of interstellar dust, but a component of a growing, solid, rocky body. A body that was itself in the process of being gathered by gravity into something larger. The largest ones had enough mass to attract others. Collisions between planetesimals were no longer gentle sticking events, but full-scale impacts, often violent, sometimes catastrophic. Planetesimals collided and merged, or collided and shattered, sending fragments in new directions to collide with other things. The inner solar system, during this period, was a chaotic place, a shooting gallery of rocky bodies in overlapping orbits, impacting each other at velocities of kilometers per second, gradually, through a combination of merging and the elimination of bodies with unstable orbits, building toward the larger objects we now call planets. I was inside one of the planetesimals that was doing the merging rather than the shattering. I was part of a body that was growing, accumulating mass from impactors, incorporating other rocky material into itself, becoming, slowly and violently, something that was beginning to have the scale and gravity of a real planetary body. Over tens of millions of years, and the collision history of the early solar system makes those years eventful ones. By any standard, the number of large bodies in the inner solar system decreased, and the size of the remaining ones increased. The process is called runaway accretion, and it is self-reinforcing. Larger bodies have more gravity, which means they attract more material, which makes them larger, which gives them more gravity. The body I was part of was growing into a planet. It was growing into the Earth. The early Earth was nothing like the Earth, you know. I want to be clear about that, because the word Earth carries associations: blue oceans, green land, white clouds, the particular living world that exists now, that are entirely absent from this early period. The early Earth was a hellish place, by any comfortable standard. Hot, largely molten, bombarded constantly by impactors from the still chaotic solar system around it. A world covered in magma oceans, with no solid crust to speak of, no liquid water on its surface, no atmosphere in any recognizable form. It had a name that geologists use for this period, the Hadean. From Hades, the ancient Greek underworld. The name is well chosen. The early Earth was, by the standards of the place it would eventually become, an inferno. The heat came from multiple sources. The kinetic energy of all those impacting planetesimals converted to heat on impact. The decay of radioactive elements incorporated into the Earth during its formation, short-lived radioactive isotopes that have since decayed away entirely, but which in the early Earth were present in quantities sufficient to generate enormous heat. And the energy released by differentiation, the process by which the Earth, once it was large and hot enough, sorted itself by density. Iron and other dense metals sinking toward the center, forming the core. Lighter rocky material rising toward the surface, forming the mantle and eventually the crust. Differentiation was one of the most important events in Earth's early history. It gave the planet its layered structure. The iron core, the rocky mantle, the thin crust that persists today. And it happened relatively quickly, over perhaps tens of millions of years, as the early molten Earth essentially unmixed itself by density. I was in the rocky material. Carbon is not particularly dense, and in the sorting process of differentiation, I ended up in the silicate portion of the Earth rather than sinking with the iron toward the core. I was in the mantle, the vast rocky layer that makes up most of the Earth's volume as the planet sorted itself out and began, slowly, to become something with structure. There is a moment I want to linger on, somewhere in this early chaotic period of Earth's history. A moment that deserves its own space in the telling. Approximately 4.5 billion years ago, give or take. The dating has uncertainties. A large body, perhaps the size of Mars, collided with the early Earth. The collision was catastrophic in scale, dwarfing anything that had come before in Earth's accretion history. The impacting body, which scientists have named Theia, after a figure in Greek mythology, hit at an angle, and the energy released was extraordinary. Both bodies were largely vaporized or melted by the impact. The cores of the two bodies merged, sinking to form the combined Earth's core. The outer rocky material was blasted outward, some of it escaping into space, most of it going into orbit around the newly enlarged Earth. That orbiting debris, over a period of perhaps decades or centuries, coalesced under its own gravity into a new body. The Moon. The Moon was made, in large part, from the outer layers of the early Earth from the same rocky material that I was part of. Some portion of the carbon that is now on Earth was surely part of the material thrown into orbit and incorporated into the Moon. Some portion, perhaps including me at various moments in the chaos of the impact, was briefly in orbit, suspended between Earth and the forming Moon, before being swept up by one body or the other. The giant impact, as it is called, was perhaps the most violent single event in Earth's history. And yet it also, ultimately, helped make Earth the place it became. The Moon's gravitational influence stabilizes Earth's axial tilt, giving us relatively consistent seasons over geological time. The tides the Moon produces have influenced the mixing of the oceans and the conditions of coastal environments. The Moon is not incidental to the story of life on Earth. It is part of the context that made life possible. I survived the giant impact. I was part of the material that ended up in the Earth rather than the Moon. And when the chaos subsided, when the worst of the bombardment eased and the Moon had settled into its orbit, and the Earth began, very slowly, to cool, I was here. On this planet. Part of it. For the first time in billions of years of wandering, I had a home. Not a comfortable home, not yet. Not a home with oceans or atmosphere, or any of the features that make Earth hospitable. Just a hot, slowly cooling, heavily bombarded rocky world, sorting itself out, beginning the long process of becoming the planet it would eventually be. But it was here. It was solid, or mostly solid, or becoming solid. It was a specific place in the solar system, orbiting a specific star, with specific properties. Its size, its distance from the Sun, its composition, the presence of the Moon. That would matter enormously for everything that followed. I had been made in a star that died before the Sun was born. I had traveled through interstellar space for longer than the Earth has existed. I had been gathered by gravity into a protoplanetary disk, incorporated into planetesimals, built into a growing planet through billions of collisions over tens of millions of years. I had survived the sorting of differentiation and the violence of the giant impact. And now I was here, on Earth, in the rock, in the mantle of a young and cooling planet, surrounded by silicon and oxygen and iron, and all the other elements that had made the same long journey from stellar cores and interstellar clouds and protoplanetary disks. Part of a world. For the first time, I had arrived. Let that settle, if you like. The long journey from a stellar core to this, to a solid planet, orbiting a star, in a solar system that is beginning to look, very slowly, like something familiar. The chaos of the early solar system is real, and was extraordinary. But underneath it, through all of it, was the patient arithmetic of gravity doing what gravity always does. Gathering, building, making something large and complex from something small and dispersed. The universe had taken a cloud of gas and dust, material scattered by countless dead stars, mixed and drifted through the interstellar medium for billions of years, and made a planet from it, made the Earth from it, made me part of the Earth. It took 4.5 billion years to get here. It took supernovae and interstellar clouds and protoplanetary disks and impacts and differentiation, and the formation of the Moon. It took physics working on physics, gravity working on matter, heat working on rock. But here we are. The Earth is young and hot, and has a very long way yet to go. And I am part of it, deep in the rock, waiting without knowing I am waiting for whatever comes next. The solar system is quiet now, or quieter. The worst of the bombardment is easing. The Sun is shining steadily. The Moon is in its orbit. And somewhere on the surface of this cooling world, something extraordinary is about to begin. But that, too, belongs to the next chapter. For now, just this. Just the Earth, new and hot and real, orbiting its star in the darkness of the young solar system. Home. Rest here a while. We have arrived somewhere, finally, after a very long journey. And the best parts of the story are still ahead. The Earth cooled. Not quickly. Nothing about this story happens quickly, and the cooling of a planet is no exception. It took hundreds of millions of years for the surface of the early Earth to transition from the roiling magma ocean of the Hadean into something that could, by any generous interpretation, be called a crust. A thin, unstable, constantly fractured and recycled surface of solidified rock, still subject to bombardment from space, still heated from below by the enormous reservoir of heat locked in the planet's interior, still far from the relatively stable surface geology we know today. But it cooled. Degree by slow degree, year by slow year, the surface temperature dropped. And as it dropped, something happened that would turn out to be one of the most consequential events in the history of the planet. Water arrived. Some of it had been here all along, bound up in the minerals of the rocky material from which the Earth formed. Some of it was delivered by comets and asteroids during the late stages of the bombardment. Icy bodies from the outer solar system, carrying frozen water that had formed in the cold reaches of the protoplanetary disk. As the surface cooled below the boiling point of water, that water, released from minerals, delivered from space, began to condense, to pool, to flow. The first rain fell on the young Earth. And then the first puddles, the first streams, the first shallow seas, and eventually, the first oceans. This matters for my story in a very direct way, because water is where things began to happen for me. In the rock of the early mantle, I had been chemically inert, locked into mineral structures, surrounded by silicon and oxygen in configurations that left little room for the kind of dynamic chemistry that carbon does so well. But water changes things. Water is a solvent, a medium in which molecules can dissolve, move, meet each other, react. Water is, in a very real sense, the medium of chemistry. And when it came into contact with the rocky surface of the early Earth, it began the slow work of dissolving and transporting and concentrating the materials it touched, including me. Carbon moves through the Earth's systems in what geologists call the carbon cycle, a set of processes by which carbon atoms are exchanged between the atmosphere, the oceans, the surface rocks, and the deep interior of the planet. It is a cycle that operates on many timescales simultaneously, from the very fast to the very slow. Carbon dioxide dissolves in rainwater, making it mildly acidic, allowing it to slowly dissolve carbonate rocks and carry carbon into rivers and eventually into the ocean. Carbon in the ocean is incorporated into the shells of marine organisms, which fall to the seafloor when those organisms die, building up layers of carbonate sediment that are eventually subducted into the mantle and returned to the surface through volcanic activity. Carbon is exhaled by volcanoes and absorbed by plants and released by the decay of organic matter and exhaled by animals and dissolved in seawater. The carbon cycle is ancient. It was operating, in some form, before life existed to participate in it. And I was caught up in it, moving from rock to water to atmosphere and back again, over millions of years, driven by the same geological processes that shaped the surface of the early Earth. I moved. I changed forms. I was carbon dissolved in seawater for a time, part of a bicarbonate ion drifting in the early ocean. I was carbon in the atmosphere, part of a carbon dioxide molecule, floating above a world that looked nothing like the one you know. I was carbon in a mineral, locked briefly into a carbonate structure in the sediment on the ocean floor. And all the while, the Earth was changing around me, cooling further, developing a more stable crust, building the first continental rock, sorting out its atmosphere, getting ready for something. Approximately 4 billion years ago, give or take, because the dating of the very earliest events in life's history is difficult and the evidence fragmentary, something happened in the waters of the early Earth. Chemistry crossed a threshold. I do not know exactly where I was when it happened. I may not have been there for the very first moment. The origin of life is not a single event with a specific location and time so much as a gradual process of increasing chemical complexity, happening in multiple places, over an extended period. But somewhere in the early ocean, or in warm shallow pools, or in the hydrothermal vents on the seafloor, where hot mineral-rich water met the cold ocean above, carbon chemistry began doing something it had never done before on this planet. It began organizing itself. Simple carbon molecules combining into more complex ones. Complex molecules forming chains and rings and structures of increasing sophistication. Certain molecules developing the ability to catalyze the formation of other molecules, to act as templates, to encourage specific reactions, to speed up processes that would otherwise be too slow to matter. And eventually, and this is the threshold, the crossing that changes everything, molecules that could make copies of themselves. Self-replication. That is the beginning of life. Not the whole of it. Life as we know it is far more elaborate than simple self-replicating chemistry. But self-replication is where the story starts. Because once you have molecules that can copy themselves, you have something that can evolve. Copies are made imperfectly. Some copies work better than others. The better working ones make more copies. Over generations, even generations of molecules, before there were any cells or organisms, something like natural selection begins to operate. Chemistry starts very slowly to become biology. I was there for this. I was part of it. I do not know in what capacity. The details of my path through these early stages of life's origin are not recoverable, even in principle. The record of those first steps is too ancient, too thoroughly reworked by subsequent geology and biology, to read in any detail. But I was part of the carbon pool from which the first biological molecules were drawn. I was in the ocean, in the chemistry, in the mix. And at some point, at some specific moment that I wish I could identify more precisely, I became part of something alive. Let me try to describe what that means. What it means for a carbon atom to be part of a living thing, as opposed to being part of a rock, or a mineral, or a gas. The difference is activity. In a rock, I was part of a crystal structure, a regular, repeating arrangement of atoms held in fixed positions by the forces between them. Stable, inert, unchanging over geological timescales, barring some external disruption. My presence in the rock did not do anything. I was simply there. In a living thing, nothing is simply there. Every molecule in a living cell is part of a process. Everything is being made or broken down or transported or transformed. The chemistry of life is not static chemistry. It is dynamic, constantly changing, constantly responding to the needs of the organism and the conditions of the environment. Molecules are assembled and disassembled. Energy is captured and released. Information is read and copied and expressed. The entire system is in constant, organized, purposeful, or at least functionally purposeful motion. And I was part of that motion. Perhaps I became part of a protein first. Proteins are the workhorses of biology, the molecular machines that carry out most of the functional work of living cells. Enzymes that catalyze reactions. Structural proteins that give cells their shape. Transport proteins that carry molecules across cell membranes. Signaling proteins that allow cells to communicate. The diversity of protein function is extraordinary, and all of it is built on the same fundamental structure. Chains of amino acids, folded into specific three-dimensional shapes. Amino acids are carbon compounds. Each one is built around a central carbon atom, my kind of atom, with 4 different groups attached to it, exploiting those 4 bonding sites I described. 20 different amino acids are used in the proteins of life on Earth, each one with a different chemical character, each one contributing something different to the proteins it becomes part of. And the sequence of amino acids in a protein determines how the protein folds, how it arranges itself in 3-dimensional space, and that folding determines what the protein can do. If I became part of a protein, I might have been in the backbone of the chain, part of the repeating carbon-nitrogen-carbon-carbon-nitrogen structure that runs the length of every protein like a thread. Or I might have been in a side chain, one of the chemical groups that branch off the backbone and give each amino acid its particular character. Either way, I would have been integral to the structure, necessary to it. One carbon atom among many, but each one counting, each one holding its part of the shape that made the protein what it was. Or perhaps I became part of DNA. DNA, the molecule that carries the genetic code. The molecule that is, in a very real sense, the blueprint of life. The instructions for building and operating a living organism, copied and passed from cell to cell and generation to generation, persisting over billions of years of evolutionary time. DNA is built on a carbon backbone. The long double helix, that famous twisted ladder structure, has two sugar phosphate backbones running in opposite directions, connected by the base pairs that encode genetic information. The sugars in those backbones are deoxyribose, a 5-carbon ring molecule. 5 carbon atoms, arranged in a ring, forming the fundamental structural unit of the backbone of every DNA molecule in every living thing on Earth. If I was one of those carbons, if I was part of a deoxyribose molecule in a DNA backbone, then I was part of something that carried information. I was one of the atoms in the scaffold that held the genetic code. And when that DNA was copied, when the cell divided and passed its genetic information to daughter cells, I would have been copied too, one of the carbons in the backbone of the new strand, continuing in a new cell, carrying my position in the structure forward into the next generation. Or perhaps I was in one of the bases, adenine or guanine or cytosine or thymine, the 4 chemical letters of the genetic alphabet. Each of those bases is a carbon-containing ring structure. If I was part of a base, then I was not just in the scaffold of genetic information. I was part of the information itself. My specific position in the molecule was part of what determined which gene was present, which protein would be made, which function would be carried out. I was perhaps part of a letter in the oldest library in the world. Life, once it had started, did not stay simple. The first living things were simple by any measure. Single cells, without the complex internal structures of the cells that make up your body, carrying out a limited repertoire of chemical reactions, persisting in environments that would be hostile to most modern life. But they were alive. They grew. They divided. They made copies of themselves. And over time, through the slow accumulation of changes and the relentless pressure of natural selection, they became more complex. The timeline is long even by my standards. The first cells, around 4 billion years ago. The first cells with a proper nucleus. The eukaryotes, the lineage that would eventually give rise to all complex life. Perhaps 2 billion years ago. The first multicellular organisms, perhaps 1 billion years ago, or a little more. The Cambrian explosion, around 530 million years ago, when the diversity of animal life expanded dramatically in what is, geologically speaking, a very short time. Fish, then land plants, then amphibians, then reptiles, then mammals, then primates, then very recently, a handful of millions of years ago, less than a single % of the Earth's total age, something that was beginning, in recognizable ways, to be human. I was part of living things throughout this time. Not always. I moved in and out of living matter, through the carbon cycle, spending time in the atmosphere and the ocean and the soil between my stints inside organisms. Carbon is not trapped in life permanently. It cycles. It moves. A carbon atom in a leaf today may be in the soil tomorrow, dissolved in a river next year, in the ocean in a century, in a marine organism in a millennium, in limestone rock in 1 million years, released by a volcano in 100 million years. I cycled. I always cycle. But I was part of living things many times over those billions of years. I was part of organisms so ancient they have no descendants. I was part of lineages that flourished and went extinct. I was part of the chemistry of evolution itself, present in the molecules that carried genetic information, the molecules that were copied and varied and selected, the molecules through which the process of life's increasing complexity expressed itself. I was there for a great deal of it. And then, at some point in the relatively recent past, recent by my standards, though ancient by yours, I became part of something new. Something that looked up. I do not know the specific moment. I cannot trace the exact path that brought me from wherever I was, a carbon atom in the soil, perhaps, or dissolved in a river, or part of the carbon dioxide in the atmosphere, into the first human body that incorporated me. The transition happened through the ordinary processes of biology. A plant absorbed carbon dioxide from the atmosphere, using sunlight to drive the chemical reactions of photosynthesis, building my carbon into sugar molecules in its leaves and stems and roots. An animal ate the plant, and the sugars were broken down and rebuilt into the molecules of that animal's body. Perhaps another animal ate that animal. And somewhere in that chain of eating and being eaten, of carbon moving from the atmosphere into plants, and from plants into animals, and through ecosystems in the slow cycling that has characterized life on Earth for billions of years. Somewhere in that chain, I ended up in a human body for the first time. And I found it remarkable, not because it was more complex than other living things I had been part of, though it was extraordinarily complex. Not because the chemistry was fundamentally different. It was the same carbon chemistry, the same amino acids and sugars and lipids, the same DNA backbone, the same fundamental biochemistry that all life on Earth shares. But because of what this particular collection of carbon and other atoms was doing with all of that complexity. It was thinking, there is nothing in my billions of years of existence that quite prepared me for this. I have been inside stars. I have been scattered by supernovae. I have drifted through interstellar space. I have been gathered by gravity into a planet. I have been part of the chemistry of the early Earth, and the chemistry of the first living cells, and the chemistry of billions of years of evolving life. I have been part of organisms that swam and crawled and walked. But thinking is something different. The carbon in your brain, in the neurons that fire as you process these words, in the synapses that connect one thought to the next, in the long carbon chains of the myelin that insulates your neural pathways and speeds the transmission of signals from one part of your nervous system to another. That carbon is doing something that, as far as we know, no carbon anywhere else in the universe is doing. It is participating in consciousness, in awareness, in the experience of being. I do not understand consciousness. No one does fully. It is one of the deepest unsolved problems in science. How physical processes, how the movement of ions through membranes and the firing of electrical signals along neurons and the complex dance of neurotransmitters across synapses gives rise to the felt experience of being a self, of having an inner life, of knowing that you exist. The hard problem of consciousness, as philosophers call it, remains genuinely hard. But I am part of it. Right now, as you listen to these words, some of the carbon in your brain is participating in the process that produces the experience of hearing them. Some of the carbon in your neurons was, long ago, in a star, was scattered by a supernova, was drifted through interstellar space, was gathered into this solar system, and this planet, and this biosphere, and this body. And now it is thinking. Now it is feeling. Now it is experiencing the astonishing fact of its own existence. I want to tell you something about what it means to be inside you specifically. You are not a static object. You feel solid. You have the persistent sense of being a continuous self, the same person you were yesterday and will be tomorrow. But at the molecular level, you are constantly changing. The atoms that make up your body are not fixed there permanently. They cycle in and out, replaced by new atoms from the food you eat and the air you breathe, exported in the carbon dioxide you exhale and the molecules you excrete. Different parts of your body turn over at different rates. The lining of your gut replaces itself in days. Your red blood cells last about 4 months. The proteins in your muscles are replaced over weeks. Your bones, which feel so solid and permanent, are constantly being remodeled, the calcium and other minerals cycling slowly in and out over years. Even your neurons, which last much longer than most of your cells, are constantly renewing their molecular components. The you of 10 years ago shared very few of its atoms with the you of today. You have been rebuilt, almost entirely, from new materials, while remaining, in every meaningful sense, yourself. The continuity is not in the atoms. It is in the pattern, the information, the specific arrangement that makes you you, encoded in your DNA, and expressed in the structure of your cells and the connections of your neurons. Atoms are the material, but you are the pattern, and I have been part of that pattern for a while. Perhaps I am in your bloodstream, right now, part of a glucose molecule being carried to a cell that needs energy. Perhaps I am in a protein in your muscle tissue, part of the fibrous structure that contracts when you move. Perhaps I am in a lipid in a cell membrane, part of the barrier that defines where one cell ends and another begins. Perhaps I am in your DNA, in one of the billions of base pairs that spell out the genetic code you inherited from your parents, and they from theirs, going back through all the generations of human ancestors, through the primates before them, through the mammals before that, all the way back to the first living things in the early ocean. Perhaps I am part of the molecule that, right now, is carrying the signal that processes these words. Perhaps I am part of the thought you are having at this moment. I do not know. I cannot see myself from the outside. I cannot trace my current location in your body with any precision. But I am here somewhere. I know that. Every breath you take contains carbon dioxide, and every breath pulls in new carbon in oxygen and nitrogen and trace gases, and the food you eat is full of carbon, and the carbon cycles through you and out of you, and the world is full of carbon going everywhere, and some of it, some small fraction of the carbon that has passed through your body in your lifetime, or that is in your body right now, was made in a star that died before the sun was born. Some of it is me, and I have been waiting a very long time, longer than you can really imagine, longer than the Earth has existed, to arrive here. To be part of something that can wonder about its own origins. To be part of a mind that can ask where it came from and, remarkably, begin to answer that question. This is what people mean when they say we are made of stardust. Not a metaphor, not a poetic flourish. A description of actual events, actual journeys, actual physics. The carbon in your body was made in a star, was launched into space by a supernova, drifted through the dark for billions of years, became part of the Earth, cycled through the atmosphere and the ocean, became part of living things, became part of you. The universe made you from its own substance, from atoms that have been part of stars and clouds and rocks and oceans, and countless living things before you. You are not separate from the history of the cosmos. You are made of it. You are, in the most literal and physical sense possible, a part of the universe that has become aware of itself. And I, one small carbon atom, one specific nucleus of 6 protons and 6 neutrons, born in a stellar fire that burned out billions of years before you existed. I am inside you. Right now. Part of you. After all of this, after everything. Here we are. It has been a long journey. From a stellar core to interstellar space. From a molecular cloud to a protoplanetary disk. From the early Earth to the first oceans. From the first chemistry to the first life. From the first life to the first complex cells. From the first complex cells to the first animals. From the first animals to the first humans. From the first humans to you. Billions of years. Countless forms. Countless bodies. Countless molecules. Countless moments of being part of something alive, and then returning to the world and becoming part of something else. And now this, the longest and strangest journey in my experience, ending here. In you. In the quiet of wherever you are, listening to these words, resting or drifting towards sleep, existing in the specific and unrepeatable way that only you exist. I am glad to be here. I am glad that the star that made me died the way it did, and scattered its contents into space. I am glad that gravity gathered that scattered material into a new solar system, a new planet. I am glad that chemistry found its way, slowly and improbably, to life. I am glad that life found its way, slowly and improbably, to complexity. I am glad that complexity found its way, slowly and improbably, to you. You are the destination of a very long journey. A journey that began in fire, passed through the dark, arrived at the earth, moved through stone and water and air and the bodies of countless living things, and ended here. With you. Breathing. Alive. Aware. Let that settle, as you settle. Let the weight of it be gentle rather than heavy. You are ancient and new at once. You are made of the oldest material in the solar system, and you are thinking thoughts that have never been thought before. You are, in every atom of you, a product of the universe's long history, and you are also completely, irreducibly yourself. The carbon in you has been many things. Right now, it is you, and that, after everything, is the most remarkable thing it has ever been. Rest now. You are home. I have been telling you my story. One atom, one journey, one carbon nucleus, born in a stellar core, scattered by a supernova, drifted through the dark, gathered into a planet, cycled through the Earth systems, incorporated into life, arriving eventually here in you. It is a long story and a true one, and I hope it has given you some sense of what it means to be made of matter that has a history. Matter that has been somewhere. Matter that carries, in its very existence, the record of events that happened long before the Earth was born. But I have been, in a sense, speaking only for myself. And I am just one atom among an almost incomprehensible number. Your body contains roughly 7 billion atoms. That is a 7 followed by 27 zeros. If you tried to count them at 1 per second, without stopping, it would take you longer than the current age of the universe to finish. The number is not just large. It is, for all practical purposes, beyond the capacity of the human mind to hold as a real quantity. And almost every single one of those atoms has a story like mine. Not identical to mine. Each atom has its own specific history, its own particular path through the universe, its own sequence of stellar cores and interstellar clouds and geological processes and biological molecules. No two atoms have had exactly the same journey. But the broad shape of the story made in a star, scattered into space, gathered into the solar system, arriving on Earth, cycling through the planet systems, becoming part of life, becoming part of you, that shape is shared by nearly everything you are made of. You are not just made of my stardust. You are made of stardust across the board. In every direction. In every element. Let me tell you about some of the others. Oxygen first, because you cannot go more than a few minutes without thinking about it. Oxygen is the most abundant element in your body by mass. More than 60% of your body's mass is oxygen, mostly in the form of water, which is 2 hydrogen atoms and 1 oxygen atom, and which makes up the majority of your body's volume. The oxygen in the water in your cells, in your blood, in the fluid that surrounds every tissue, all of that oxygen was made in stars. Oxygen is, like carbon, a product of stellar nucleosynthesis. It is made primarily in the helium-burning cores of massive stars, through a reaction that takes a carbon nucleus or atoms like me, and adds another helium nucleus to it, producing oxygen-16, the most common form of oxygen. This is the same process I mentioned earlier, the reaction that I was constantly at risk of undergoing in my own stellar core. The reaction that would have converted me from carbon to oxygen had the specific collisions gone slightly differently. Many of my fellow carbon atoms did undergo that reaction. Many of them became oxygen. And that oxygen, like me, was scattered by supernova explosions into interstellar space, gathered into the protoplanetary disk of our forming solar system, incorporated into the Earth, cycled through the atmosphere and the oceans, and eventually incorporated into living things. The oxygen you are breathing, right now, the oxygen molecules moving through your lungs, crossing into your bloodstream, being carried to your cells, participating in the chemical reactions that release the energy that keeps you alive, that oxygen was made in stars, was launched into space by stellar explosions, spent billions of years wandering through the galaxy before arriving here. Every breath is, in a very real sense, an act of communion with the long history of the cosmos. Now consider the nitrogen in you. Nitrogen makes up about 3% of your body's mass, which sounds modest until you consider what it is doing. Nitrogen is in every amino acid, the building blocks of every protein in your body. The amino group that gives amino acids their name, the group that connects one amino acid to the next in a protein chain, contains nitrogen. Nitrogen is in every base in your DNA: adenine, guanine, cytosine, thymine. all 4 of the genetic letters that encode everything about your biology. All of them contain nitrogen atoms in their ring structures. Without nitrogen, there are no proteins. Without proteins, there is no biology. Without nitrogen, there is no DNA. Without DNA, there is no genetic code, no heredity, no evolution, no life as we know it. And nitrogen was made in stars. Nitrogen is produced through several pathways in stellar nucleosynthesis, including the CNO cycle, a set of nuclear reactions that uses carbon, nitrogen, and oxygen as catalysts for converting hydrogen into helium in the cores of stars more massive than our Sun. Carbon, nitrogen, and oxygen are cycled through this process, each one being created and consumed and recreated in a chain of reactions that ultimately produces helium and releases energy. The nitrogen produced by this and other processes accumulates in stellar interiors and is eventually scattered into space by stellar winds and supernovae. The nitrogen in your DNA in the bases that encode your genes, that carry the information that has been passed from parent to child through every generation of your ancestry, going back through all the forms of life that preceded you to the very first living things in the early ocean, that nitrogen was made in stellar interiors, was scattered into space, was gathered into this solar system, was incorporated into your body through the food you eat and the air you breathe. Your genetic code is written in stardust. Iron is the element I want to talk about next, because iron has a special place in the story of stellar nucleosynthesis. I mentioned it before. Iron is the endpoint of stellar fusion, the element at which the energy economics of nuclear reactions change fundamentally, the element that accumulates in the cores of massive stars until they can support themselves no longer and collapse into supernovae. Iron is, in that sense, the element that kills stars. And it is also an element that you absolutely cannot live without. There are about 4 grams of iron in your body, roughly the mass of a small nail. Most of it is in your blood, specifically in the hemoglobin molecules that give your red blood cells their color and their function. Hemoglobin is a protein, and at the center of each hemoglobin molecule is a structure called a heme group, and at the center of each heme group is a single iron atom. That iron atom is what binds to oxygen. It is the iron that captures oxygen in your lungs and holds it while your blood carries it through your arteries to every tissue in your body, and then releases it where it is needed. The iron in your blood is what keeps you alive, breath by breath. And that iron was made in the core of a massive star, in the final stages of its life, by the progressive fusion of lighter elements into heavier ones. It was there, in the stellar core, accumulating, right up until the moment the star could no longer support itself. And then the star exploded, and the iron was scattered into space along with everything else, and eventually it found its way into the interstellar medium, into the protoplanetary disk of our solar system, into the Earth, into the chemistry of biology, into hemoglobin, into blood, into you. Every heartbeat is powered, in part, by iron that was forged in the death throes of a star. Calcium is next, and calcium's story is worth telling, because calcium is everywhere in you, and its presence is so fundamental that you would literally fall apart without it. About 1 kilogram of the mass of your body is calcium. The vast majority of it is in your bones and teeth. Calcium phosphate minerals forming the hard structural matrix that gives your skeleton its rigidity. But calcium is not only structural. It is also a signaling molecule of enormous importance in biology. The movement of calcium ions across cell membranes is one of the fundamental mechanisms by which cells communicate. Muscle contraction depends on calcium. When a nerve signal reaches a muscle fiber, it triggers the release of calcium ions, and those calcium ions are what cause the muscle proteins to slide past each other and contract. Your heartbeat is regulated by calcium. Your neurons fire in response to calcium signals. Calcium was made in stars. Specifically, it is produced in the later stages of stellar fusion, in the carbon-burning, neon-burning, and silicon-burning stages that massive stars go through as they race toward their final collapse. It is produced in supernova explosions themselves, where the extreme conditions briefly available in the shockwave drive nuclear reactions that build elements that could not be produced in the earlier, calmer stages of stellar burning. The calcium in your bones, the calcium that makes your skeleton solid, that lets you stand and walk, that has been with you since before you were born, deposited in your developing skeleton while you were still in the womb, was scattered into space by one or more stellar explosions, made its way into the molecular cloud that became our solar system, was incorporated into the Earth, eventually entered the biosphere, was taken up by living things, was passed through food chains, and arrived in the cells of your body. You stand upright on stardust. I could go on. I could tell you about phosphorus, present in your DNA backbone, in the ATP molecules that carry energy throughout your cells, made in massive stars and scattered by supernovae. I could tell you about sulfur, in some of your amino acids, in the molecular bridges that give proteins their three-dimensional shape, forged in stellar interiors and distributed into the galaxy by stellar winds and explosions. I could tell you about magnesium, at the center of every chlorophyll molecule in every plant, the element that makes photosynthesis possible, made in stars and scattered into space. Every element in you has this history. Every element in your body, heavier than hydrogen and helium, was made in a star, was scattered into space, arrived here after a long journey through the galaxy, became part of the chemistry of life, became part of you. The exceptions are minor. The hydrogen in your body, and there is a great deal of it, in the water that makes up most of your mass, and in the organic molecules of your cells, was not made in stars. Hydrogen is original. It is primordial. The hydrogen in you dates back to the first few minutes after the Big Bang, forged in the primordial nucleosynthesis of the very early universe. In that sense, the hydrogen in you is older than stars, older than galaxies, as old as the universe itself. You are made, in your hydrogen, of something that formed in the first moments of creation. And you are made, in everything else, of things that stars built over billions of years and gave to the galaxy when they died. I want to say something about what the word recycled means in this context, because it is a word that sometimes carries connotations of something secondhand, something used, something that has been through other hands and is now passing through yours, diminished by the journey. The atoms in your body are recycled. That is accurate. They have been part of other things before you. They have been inside stars and scattered through space, and incorporated into rocks and oceans, and living things and soils and oceans again. They have been through an enormous number of hands, so to speak, before arriving in yours. But they are not diminished by this. That is the crucial point. An atom does not wear out. It does not become tired or depleted by being used. A carbon atom that has been inside a billion different molecules is exactly as good as a carbon atom that has never been part of anything. The 6 protons are still there. The 6 neutrons are still there. The electrons still occupy their orbitals in exactly the way they always have. The chemistry I can do is exactly the chemistry I could always do. The bonding sites are not used up. The potential is not reduced. Atoms are, in this sense, eternal, or as close to eternal as anything in the physical world comes. The atoms in you are not secondhand. They are ancient and perfect and unchanged in their fundamental nature by everything they have been through. They have visited more places and been part of more things than you can imagine. And now they are here, in you, doing the work of keeping you alive and conscious and present. They are not less for having traveled. They are, if anything, more. There is a thought I find myself returning to when I consider the full picture of what the atoms in a human body represent. Not just one element, not just my story, but all of it together. The oxygen and the carbon and the nitrogen and the iron and the calcium and the phosphorus and the hydrogen and all the rest. Each one has a different history. Different stars, different explosions, different paths through the interstellar medium, different routes through the chemistry of the early Earth and the biology of life. Some of my fellow atoms in your body were made in the same star I was made in. Some were made in stars much older than my parent star. Some were made in the relatively recent past, cosmically speaking, in stars that lived and died while complex life was already flourishing on Earth. Some arrived on Earth with the original material of the protoplanetary disk. Some arrived later, delivered by comets and asteroids during the period of heavy bombardment. You are, in your atomic composition, a gathering point for the histories of many stars. A convergence of journeys that began in different places, at different times, under different conditions. The universe's long project of building complexity, of starting with hydrogen and helium and slowly, over billions of years of stellar evolution, building up the full range of elements, is expressed in you. In the specific mixture of atoms that makes up your body. You are not made of any one star's legacy. You are made of the galaxy's legacy, of the accumulated output of billions of stellar lives, each one burning for millions or billions of years, each one building elements in its core, each one eventually scattering those elements into space to join the common pool of the interstellar medium, each one contributing something to the mixture that eventually became you. You are the product of an enormous collective effort, an effort that was not intentional, not directed toward any goal, not aware of itself, but an effort nonetheless, in the sense of something that happened over vast timescales through the operation of physical laws, something that built toward increasing complexity, something that ultimately produced the conditions under which beings like you could exist and wonder about it all. I want to take a moment with the iron in your blood specifically, because there is something in that particular detail that I find almost unbearably poetic, though I know poetic is not quite the right word for what an atom can find anything. The iron in your hemoglobin, the iron that holds oxygen, the iron that is responsible, at this very moment, for carrying oxygen from your lungs to every part of your body, including your brain, where the oxygen is used to release the energy that powers the thinking you are doing right now. Iron is the element that kills stars. It is the endpoint of stellar fusion, the product that accumulates until a star can no longer sustain itself, the element whose presence in the core triggers the catastrophic collapse that produces a supernova. Iron is, in the story of stellar physics, the element of endings, the element of death, and it is the element that, in your blood, sustains your life. The element of stellar death has become the element of biological life. The thing that ended stars has become the thing that keeps you breathing. The universe has a way of repurposing things, of taking what was used for one purpose and finding another purpose for it entirely. The stellar forge becomes the source of planetary material. The supernova explosion becomes the seed of a new solar system. The iron that accumulated until it killed a star ends up carrying oxygen in the blood of a creature that breathes. Nothing is wasted. Nothing is truly lost. Everything becomes something else, given enough time. You are breathing right now. Slowly, probably, if you are listening to this in the way this is intended. In a quiet place, perhaps in the dark, perhaps on the edge of sleep. Your breath is moving in and out. Your heart is beating. Your blood is circulating. Your neurons are firing. And all of it is being done by atoms that are older than the Earth. Atoms that came from stars. Atoms that have traveled billions of light years and spent billions of years drifting through the dark to be here, in this arrangement, in you doing this. The oxygen entering your lungs was made in a stellar core. The carbon in the cells of your lung tissue was made in a stellar core. The iron carrying that oxygen to your brain was made in a stellar core, perhaps a different one, perhaps the same one. The calcium in the ribs that expand to let your lungs fill was made in a stellar core. The nitrogen in the proteins of your diaphragm, the muscle that drives your breathing, was made in a stellar core. A single breath, in and out, involves the coordinated action of matter from the deaths of multiple stars. You breathe, and you are briefly holding inside you the legacy of suns that burned out before the Earth existed. Then you breathe out, and you return some of it to the world. And the cycle continues. The carbon cycling through the atmosphere, the oxygen cycling through the biosphere, the iron cycling through blood and soil and rock. Everything moving, always being exchanged and repurposed and incorporated and released. The universe breathing, in a sense, through you. I am just one part of all of this. One carbon atom, one voice among the billions of atoms that could tell their own version of this story. Each one with its own history. Each one with its own journey across the galaxy. Each one now here, in you, doing its specific part of the work of keeping you alive. We do not speak, the other atoms and I. We do not compare notes on where we have been. We simply do what atoms do, which is interact with each other through the fundamental forces of physics, forming and breaking bonds, moving electrons, transferring energy, doing chemistry. But if we could speak, if all the atoms in your body could somehow gather and tell their stories simultaneously, the hydrogen from the early universe, the carbon from stellar cores, the oxygen from helium burning, the nitrogen from the cyano cycle, the iron from the death throes of massive stars, the calcium from supernova explosions, the phosphorus and sulfur and magnesium, and all the rest. The sound would be enormous. A chorus of histories, each one billions of years long, each one beginning in fire and passing through the dark and arriving here. A sound so large and so old that no ear could hold it. And at the center of all of it, quiet and still and listening, would be you. Made of all of it. Made of all of us. Rest, if you can, with that thought. Not as a heavy thing. Not as something that requires any effort to hold or understand or respond to. Just as a quiet truth, settling gently into the background of wherever you are right now. You are ancient. Every part of you. The atoms in your body were already old when the earth formed. They were already travelers. Already veterans of journeys you cannot imagine. They came to you from the furthest reaches of the galaxy's history, through channels of stellar death and interstellar drift and geological cycling and biological evolution, and they arrived here, in this specific arrangement, at this specific moment. And together, they are you. Not just stardust, not just recycled matter, not just ancient atoms in a temporary arrangement, but you, thinking, feeling, aware, present. The universe made something remarkable when it made you. It used everything it had. It took the longest possible time. And here you are. Here we all are, all the atoms that make you up, gathered from the far ends of the galaxy and the deep reaches of time, present in this moment, in this body, in this life. Every one of us glad, in whatever way atoms can be glad, to be here. Every one of us home. We have come a long way together. From the first moments of my existence in the core of an ancient star, through the violence of a supernova and the long quiet of interstellar space, through the formation of a solar system and the cooling of a planet, through the origin of life and the long unfolding of biological evolution, to here. To you. To this moment, wherever you are, whatever quiet you have found for yourself tonight. It has been, by any measure, an extraordinary journey. And I am aware that it might feel, in retrospect, like the kind of story that could only be told with the benefit of imagination. A narrative constructed for beauty and meaning, rather than discovered through evidence. The kind of thing that is perhaps true in spirit, you might think, but not necessarily true in the rigorous, verifiable, scientific sense. I want to spend this last part of our time together telling you why it is true in exactly that sense. Why this is not poetry dressed as science, but science that happens to have the depth and sweep of poetry. Why we know what we know about where atoms like me come from. Why the story I have told you is not invention, but reconstruction. Not myth, but memory. The universe has a memory, and we have learned, slowly and painstakingly, how to read it. Let me take you back to the night sky. Not the sky as you might ordinarily think of it, a backdrop, a setting for the moon and the occasional planet, a source of light pollution in cities, or a field of stars in darker places. But the sky as it actually is, as what it actually contains. Every point of light you can see with the naked eye is a star and nuclear furnace, a stellar engine, a place where gravity and nuclear physics are locked in the long, slow conversation that produces light and heat, and, in the cores of the more massive ones, new elements. Every one of those stars has a history. Every one of them is, in a sense, a document, a record, a piece of evidence about the history of the galaxy and the history of matter. The question is how to read them. The answer, as I described early in our conversation, is light. Always light. The light that stars emit carries, encoded in its spectrum, the chemical fingerprint of everything in the star's atmosphere. The specific wavelengths that each element absorbs and emits the spectral lines that are as unique to each element as a fingerprint is to a person are present in starlight, readable by instruments of sufficient precision, interpretable by scientists who have spent careers learning what those patterns mean. But the reading of starlight is not just a matter of identifying which elements are present. It is more subtle than that. It is more powerful. Because what astronomers can read in the spectra of stars is not just a list of elements but a ratio, a proportion. How much of this element relative to that one? How much iron relative to hydrogen? How much carbon relative to oxygen? How much europium relative to barium? Those ratios are not arbitrary. They are not random. They carry information about how the star formed, about what material was present in the gas cloud from which the star condensed, about what kinds of stellar explosions had occurred in the neighborhood before that star was born, about what stage the chemical evolution of the galaxy had reached at the time and place of the star's formation. The ratios are, in other words, a record of history, a record that the star has been carrying in its light for billions of years. The oldest stars carry the oldest records. This is the fundamental insight of stellar archaeology. The stars that formed earliest in the history of the galaxy, the metal-poor stars, the ancient survivors that have been burning slowly and dimly for 10 or 12 or 13 billion years. Those stars formed from gas that had been enriched by only a small number of earlier stellar generations. They formed when the galaxy was young, and the cycling of matter through stars had only just begun. And so their chemical composition reflects that early state. Low in heavy elements, carrying the specific ratios of the earliest stellar explosions, preserving in their spectra the chemical signature of the first generations of massive stars that lived and died before them. When an astronomer points a telescope at one of these ancient stars and spreads its light into a spectrum, they are looking at a message from the early galaxy. A message written in element ratios, encoding information about stellar events that happened long before the Sun existed, long before the Earth existed, long before there was any life to observe any of this. The star has been holding that message for billions of years. And only now, only in this recent sliver of cosmic time, during which human beings have developed the instruments and the theory needed to decode it, is anyone reading it. The work of stellar archaeology is painstaking, patient. It requires spectrographs of extraordinary precision, capable of measuring the abundances of dozens of different elements in a single star with high accuracy. It requires large surveys, not just the careful study of one or two ancient stars, but the systematic analysis of thousands or tens of thousands of them, building up a picture of how chemical abundances vary across the galaxy and across cosmic time. It requires theoretical models of nuclear physics and stellar evolution and galactic chemical evolution, sophisticated enough to predict what the chemical signatures of different kinds of stellar explosions should look like, so that those predictions can be compared to observations. It is, in short, science at its most careful and most ambitious. Science in the business of answering some of the largest questions that can be asked. Where did the elements come from? How did the galaxy's chemical composition evolve over time? What kinds of stars, dying in what kinds of ways, produce the atoms that now make up the world around us? And the answers that have emerged from this work are answers that I find extraordinary. Not because they are surprising. In many ways, the broad outlines of nucleosynthesis theory were established decades ago and have been confirmed repeatedly by observations since. But because of what they mean. Because of what it means that we know them. It means that the story I have told you tonight is not a story someone made up. It is a story that was recovered, reconstructed from evidence, read from the light of ancient stars by human beings who devoted their working lives to the patient, careful, rigorous project of understanding where everything came from. Consider what that means for a moment. A star explodes. It scatters its contents into space. Those contents drift through the interstellar medium for billions of years, mixing with other stellar ejecta, slowly losing any obvious connection to their source. Eventually they are gathered into a new star, a different star, in a different part of the galaxy, formed billions of years after the original explosion. That new star carries, in its chemical composition, a faint imprint of the explosion that preceded it. A signature in its element ratios that encodes information about the mass and type of the star that exploded, the conditions of the explosion, the elements produced. And then, billions of years later, a human being builds a telescope and a spectrograph and points them at that star and measures the light and reads the ratios and does the mathematics and recovers, from those measurements, information about the explosion that happened billions of years ago in a star that no longer exists. The explosion left a record. The record survived, encoded in the chemistry of a subsequent star. And the record was read. The past is not gone. It is present, in the light of stars, waiting to be read by anyone patient and skilled enough to learn the language. Stellar archaeology is still a young field, in the sense that the most powerful tools for doing it are recent. The large spectroscopic surveys that have mapped the chemical composition of hundreds of thousands of stars across the galaxy, surveys with names like Gola and Apogee and Gaia Yeso, are products of the last decade or two. The theoretical frameworks for interpreting what those surveys find are still being refined. The picture of galactic chemical evolution that is emerging from this work is more detailed than anything that existed a generation ago, and it will be more detailed still a generation from now. There are questions still open. The precise sites of production of some elements are still debated. The relative contributions of different types of stellar explosions to the overall chemical budget of the galaxy are still being worked out. The history of the Milky Way, its mergers with smaller galaxies, the different star formation histories of its various components, the way chemical abundances vary across its structure is still being reconstructed, piece by piece, from the evidence preserved in stellar spectra. It is ongoing work. Science in progress. A conversation between observers and theorists and instrumentalists, conducted over decades, gradually sharpening the picture of where everything comes from. And every refinement of that picture is a refinement of my story. Of your story. Of the story of every atom in your body that came from a star. I want to tell you something about the scientists who do this work, because I think they deserve a moment in this telling. They are, in many cases, people who spend long nights at telescopes in remote locations, mountaintops, desert observatories, places chosen for the darkness and clarity of the sky. They spend long days in front of computers, analyzing data, writing code, building models. They publish papers that are read by small communities of specialists, debated at conferences, refined by subsequent work. The pace is slow, as the pace of science usually is. Progress is incremental. Breakthroughs are rare. And what they are doing, in all of this patient and unglamorous work, is recovering the biography of the galaxy, reconstructing the history of stars that died billions of years before the Earth existed, tracing the journeys of atoms from stellar cores to the interstellar medium to new solar systems, and eventually to living things. They are telling my story, and the story of every atom in your body. They do not think of it that way, necessarily. Science is not usually framed in those terms. It is framed in terms of data and models and uncertainties and peer review. But underneath the machinery of the scientific process, underneath the spectrographs and the surveys and the theoretical frameworks, is something that I find genuinely moving. People trying to understand where things come from. People asking, with whatever tools they have, the oldest and deepest question that a mind can ask. Where did all of this come from? How did we get here? What is the history of the matter that makes us up? And slowly, carefully, rigorously finding out. The fingerprints are everywhere, once you know how to look. In the spectra of ancient stars, the ratios of elements encoding the history of the explosions that seeded the galaxy before those stars were born. In the composition of meteorites, ancient rocks from the early solar system, some of them containing grains of material that predate the sun itself, microscopic time capsules carrying isotopic signatures from the specific stars that made them. In the cosmic abundances of elements throughout the universe, the overall pattern of how much of each element exists reflecting the collective output of billions of years of stellar nucleosynthesis. In the chemical gradients of the Milky Way, different regions of the galaxy having different chemical histories, different abundances, different records of their particular star formation histories. And in you, in your body, in the specific mix of elements that makes you up carbon and oxygen and nitrogen and iron and calcium and phosphorus, and all the rest the accumulated output of stellar nucleosynthesis across billions of years of galactic history. Your body is itself a kind of record, a sample of the chemical inventory of the part of the galaxy where you formed. A data point in the great reconstruction project of stellar archaeology, if only it could be read in the right way. You carry the history of stars in your bones and your blood and your DNA. You are, in your atomic composition, evidence of everything that had to happen for you to exist. And so I want to bring us back, at the end of all of this, to where we began. To the question that stellar archaeology asks. To the mystery that I mentioned in the early parts of our conversation. The mystery that seemed, perhaps, abstract at the time. How can we know where atoms come from? How can we trace the history of matter across billions of years and billions of light years? How can we read the biography of something as small as an atom, or as vast as a galaxy? The answer is the fingerprints. The chemical signatures preserved in the light of ancient stars. The isotopic records locked in ancient meteorites. The patterns of abundance that encode, in the language of nuclear physics, the history of every stellar explosion that contributed to the chemistry of the galaxy. By reading those fingerprints, astronomers have reconstructed something remarkable. Not just the history of element creation in the abstract, not just a theoretical account of nucleosynthesis, but the actual specific, step-by-step story of how the matter that makes up you and everything around you came to exist and to arrive here. They have recovered the biography of atoms. My biography. And yours. I have been a carbon atom for a very long time. I have been inside stars and inside space, and inside rock and inside water, and inside living things of kinds that no longer exist. I have been part of molecules that encoded genetic information for organisms that lived and died hundreds of millions of years before you were born. I have cycled through the atmosphere and the ocean more times than I can count. I have been buried in rock and released by volcanic eruptions and dissolved in rainwater and carried down rivers to the sea. And I have been, through all of it, exactly what I am. 6 protons, 6 neutrons, the same nucleus unchanged, that was assembled in a stellar core billions of years ago. The same atom, carrying the same potential, the same 4 bonding sites, the same chemical identity, through everything that has happened to me and everything I have been part of. I am old. I am ancient. I am, by the standards of everything that lives on the surface of this planet, almost incomprehensibly so. And right now, I am inside you. In whatever cell, whatever molecule, whatever specific corner of your biology I currently occupy. After all of that, after all the time and all the distance and all the forms I have taken, I am here. Part of you, doing whatever small part of the work of keeping you alive that falls to me in this moment. It is, of all the things I have been part of, the most extraordinary. Your carbon atom was born in a star. It traveled through the darkness of space. It survived the death of a sun. It helped build a planet. It cycled through rock and ocean and air. It became part of the chemistry of life, and life used it to build molecules of increasing complexity over billions of years of evolution. And eventually, through the long chain of causes and effects that connects the death of an ancient star to the life of a living person, it became part of you. That is the journey. That is the story. And stellar archaeology, the patient, rigorous, ongoing work of reading the chemical fingerprints preserved in ancient starlight, is how we learned it. How human beings, in just a few generations of scientific work, recovered the biography of matter, traced the history of atoms from stellar cores to living bodies, asked where everything came from, and found, in the light of distant stars, an answer. Not a complete answer. Science is never complete. There are still chapters of the story being filled in, still details being refined, still questions being asked that have not yet been answered. The work continues. The fingerprints are still being read. But the broad outlines are clear. And they are, in their broad outlines, astonishing. You are made of stars. Not metaphorically. Not poetically. Literally. The atoms in your body were forged in stellar cores and scattered by stellar explosions and gathered by gravity into this solar system and this planet and eventually this body. The universe used the deaths of ancient suns to build the materials from which you are made. It took billions of years. It required the lives and deaths of multiple generations of stars. It required the patient cycling of matter through interstellar clouds and protoplanetary disks and geological systems and biological processes spanning most of the age of the Earth. And at the end of all of it, it made you. So rest now. Rest in that knowledge, held gently, without needing to understand every detail or hold every timescale clearly in mind. Just the broad shape of it. The arc of it, from beginning to here. Fire and darkness, and a long journey and home. Let your breathing slow. Let the weight of your body settle. You are, in your atoms, one of the oldest things in the solar system. And you are, in your awareness, something entirely new. Something the universe had not managed before. Something it took billions of years to build toward. Old matter, newly arranged into something that can wonder at itself. The stars that made you are gone. They burned out long before the sun was born, long before the earth cooled, long before the first living thing drew the first breath in the first ocean. But they left behind everything they had made. They gave it all to the galaxy. And the galaxy, over billions of years, gave it to the solar system. And the solar system gave it to the earth. And the earth gave it to life. And life gave it to you. You are the current resting place of matter that has been traveling for almost as long as the universe has existed. You are the latest chapter in a story that began in the first stars. You are, in your every atom, the universe's long effort to build something complex and aware and alive. And tonight, for a little while, that effort is resting. Quietly. Here. In you. Good night.